So you have all the equations and all the derivations. I think for the first class, we don't have to go through all of them. So, but I wanted to talk a little bit about some of the intermolecular forces. So when you're doing molecular measurements, where are the forces coming from? What are we measuring? And how do we actually quantify these things? But before I did that, I wanted to know if have all the groups picked their topics. I think we wanted to go over the groups and their topics from yesterday. So, is there any? Maybe we'll go in order because where there were numbered. So, group 1. Who is group 1? Have you picked your topic area yet? Okay. Oh, that's fine. Just 1. But on which, so more like a technique kind of paper. Okay, cool. Good. One group. Okay, group 2. We're going to go in order. Everybody has to go. Who's group 2? Excellent. I feel like the front row shouldn't always be the ones having to present. Who else is in group 2? You're not by yourself, are you? Okay. See, now we'll go to that. Who wants to present? Who wants to say what, like one sentence? Which topic did you pick? You're still looking. Okay. So I think by afternoon, if you can pick, you don't have to find a paper. Just if you pick a topic area, I can help you narrow down to like a good paper. But find something you're excited about. So, okay, how about group 3?
Group 3, members of group 3.
Excellent. Did you? Yeah. Okay. Oh, great.
We will be discussing about combined inhibitory effects of
Can you be
Okay,
louder?
a little bit louder.
combined inhibitory effect of citrulline, ochratoxin, and levothyroxine on cooperative channel.
You already picked a paper then.
Actually, it's my paper only. So
That's cheating. No.
So what is the nanomechanics part you are going to test?
nanomechanics, like it's a simulation is the some in vitro studies is the. I mean, it's a aquaporin membrane channel.
Right.
So it's a
But are they studying the mechanical property?
no, actually, we did the mechanism, intermolecular interactions, and
No,
the
mechanics part.
mechanics part of it.
So we expect
But yeah, we can find.
whatever the concept we learned, we want to recall to these papers and see whether try to have some concepts related to nanomechanics. You can talk about this additionally.
Yeah.
We are interested to hear about your work.
Yeah.
We will encourage you to talk about your research. That's applicable to everybody.
Yeah.
Even an external person, if you want to talk about your research, we are always open for knowledge.
Okay, so that's 3, 4.
We have chosen the topic about nanomechanical changes in diabetic amyloid.
That's have you found the paper? Yeah, I think I read that. Good paper. 5. Yes. Okay. Oh, that's cool. So like it's a biomimetic material trying to copy what natural material, natural tissues do. Yeah, that's a good area. That's a big area of research actually, is making biomimetic materials that have the right characteristics. Yeah, great. 6? Yeah. there aren't that many papers in that area, so it's a good, it's an emerging field. Yeah, no, I think that's a good, well, of course, yeah, just make sure everybody's agreeing. 7?
Group 7?
Yeah. Okay, so like talk amongst yourselves and say, I won't say your favorite disease or favorite organ, or because you know nobody really has a favorite, but something that's exciting to you. 8? Yeah.
We have a lot of topics we are going to network, but we choose the role of cellular aerodynamics.
Quick. Yeah, so that's there's a lot of papers. The 2 that you'll have tonight is on breast cancer. I would, because if you start looking just like nanomechanics, cells, cancer, there's a lot of papers. I would narrow it down to a particular cancer type. Otherwise, it might be a little overwhelming. But yeah, good. Where are we at? 9?
Group 9?
You haven't chosen one yet? Okay, so we'll check in with those groups in the afternoon. 10?
So we'll be discussing about age-related nanostructure, nanomechanical changes in the cartilage artery.
Ah, hey, I know that paper. Is it one of my papers or is it who's on the office?
None of them able to pick that today.
No, because it's not me.
No.
Okay, so I know who it is though. Then. It's a good paper. They're very nice people. Yeah. No, good paper. 11.
Now, we'll be speaking about nanomechanical recognition of the N-methyl ammonium salts.
Cool. I don't know anything about that. That's cool. Yeah. That's a sensor type thing. That's really cool. Awesome. And then 12, right? We had 12 groups. Yeah. Yeah. Kind of like the bone cartilage interface. Cool. Everyone, so that, you know, we're all going to end up with arthritis or osteoporosis, so we should all pay attention to those. Okay, so for the groups that haven't picked topics, maybe, you know, over lunch talk and at least kind of narrow down what you want to do so that after lunch we can check and make sure everybody has a topic area. And then also before I started, I wanted to know if anyone had questions about any of the materials so far. I think someone had emailed me a question and I hadn't had a chance to answer it yet, so pull it back up. But does anyone have any other questions before I pull up the one that? Oh, I can't find the one. Someone emailed me a question and I hadn't had a chance to answer it yet. I was going to answer. Yeah. What was your question? Okay, so good. Anybody else? Yes?
In the paper that you have sent yesterday, there was a point that cancer cells lose their elasticity, they turn rigid. So if possibly they turn rigid, that would be easy targets for the drug. Then why does resistance develop to remove such rigid cells?
Right, so that was the paper where they were looking at drug-resistant cells, or which of the two? Sorry. They were looking at, so you have a change in mechanical properties with drug-resistant versus not drug-resistant. So there's two kind of conclusions from that. The first, I don't know, if not everybody has seen the paper yet, I think.
No, someone not get paper, ma'am.
What?
I didn't get paper.
Yeah, they're sending them now. So we might hold that question so everybody has a chance and we'll get back to it tomorrow morning, because that's actually one of the very interesting things. That's why I picked those papers. It's an interesting discussion, and it also is a nice way to, you can see the differences in the mechanical property of the different cells, both in terms of when they're tumor cells and metastatic, and then the other one is with drug resistance. And it's a an interesting basic science thing, but it actually also has implication for drug targeting and drug therapy. So we'll talk about it tomorrow morning, but remind me if I don't, the question. Anybody else? Yes?
What are the different types of mechanical interactions of a cell other than the ECM and the neighboring cell?
Oh, there's a lot. So the big ones usually are cell-cell and cell matrix interactions, but that's for most of the cells that are adherent cells. So like a red blood cell is not adherent, it floats around. So there's a lot of interactions that happen with soluble factors and proteins, as well as we're finding out more and more that there's extracellular vesicles. So, cells throw out things in little packages, and then cells on the other end will receive them. And actually the pretty video of inside the cell showed an animation of that happening, right? Vesicle, the cell interacting with that and fusing. And there's different mechanisms of how that occur. So there's actually a lot of work in that area, as well as cell, how a virus gets into a cell, those kinds of things. So the big ones for like kind of maintenance of structure, as well as intracellular kind of communications that we think about tend to be cell matrix, cell-cell interaction, but that's not to take away from the fact that there's a lot of other interactions that occur, and they're very cell type specific. So the cardiac myocyte, do you know those in my labs? It has a lot of, most of its function tends to be cell-cell, because it's trying to contract together. So that's what most of the focus of research has been on, but there's been recent studies that have shown that after a heart attack, some of these kind of vesicles and things that send out cues and signals actually interact and change cell mechanical properties as well. So it's kind of a more emerging field in those cells, but in other cell types, because that's more of their function, people have studied it more. So it's a little bit depends on the cell type. That's a good question. Yeah?
I have a very basic question. So all these characteristics in our studies will focus on, so now we have advanced for studying even a single cell mechanics. But I want to know whether it's possible to study the mechanics of the whole system.
Yes.
Organism, or an organ.
Yeah.
Then in vivo condition, not like the isolation or to bring like this and this.
Yeah.
That will be, it's very complex, because multifactorial and multi-equations. But is it possible to study?
Yeah. So yes and no. So most of the basic studies have been, you take the cell out, you isolate it, you look at it. You take the matrix out, you isolate it, you look at it. But obviously, when they form a tissue, it's a lot more complex. So in terms of how to bridge that gap, and we'll talk a bit about, I think it's this afternoon. It's either this afternoon or tomorrow. I can see the slide, I just don't remember if it's today or tomorrow. So computational modeling is nice for helping bridge that gap. It's hard to get nano scale forces and interactions on a large piece of tissue. Some of the higher resolution, super resolution optical microscopy techniques are trying to get at that, because you can use it on a large piece of tissue. One of the techniques that I will show today is traction force microscopy and those kinds of things, where, so in a cell experiment, you have them on a dish and you're looking at imaging changes and then relating that to mechanics. People can do that with whole tissue. It's actually using optical mapping techniques. So you have one frame of an image and the next frame of the image, and between the two you deform. And if you know the mechanical properties of the stuff that deforms, you can map out where the stresses and strains are. In vivo in people, the easiest way to get some assessment of mechanical properties of tissues and things in a person is with ultrasound, because ultrasound fundamentally is kind of a mechanical technique. So there are certain studies where they do, push on things, measure with ultrasound, and other like live imaging techniques, but it's difficult. So a lot of those studies get done in larger animal models. You can actually embed sensors in a sheep or something like that to get some more data, but it's difficult. And so that's where the modeling approaches are nice, because you can get small scale experiments, and then you can do traditional large scale testing where you don't have that information, and you can see with the model, if I assume the things I had in my experiment at a small scale, and now I scale it up in the computer, do I get the properties that I measured? And so, and of course, the answer is not exactly. And the question is, when you get it not exactly, what's the difference? So that's most of the work they do. That's a good question. Anyone else? Okay, so on the molecular side, there's lots of things we can measure, and the data we had yesterday was looking at molecular unfolding and binding. For polling of molecules, there are several models, and I don't have those in the slide, but if you were doing those experiments, if you have a long polymer that's like just a long string, there's a model called the worm-like chain model. There's a couple other variants of that if you have more structure to the string. So if you ever do those experiments, that's how you fit the data to get parameters from it. What I wanted to talk about today was more generic forces that always are present and that you'll always have in those experiments, and how to interpret them. So again, just to remind you, right, there's all sorts of different bonds and things that you could be measuring, and it depends on the system. So one of the issues I think that happens a lot with AFM, optical tweezers and everything, you have your experiment, you set it up, you get data. You get lots of data, right? Because we know we have to do it lots of times, you get lots and lots of data, and then what do you do with the data? And so kind of understanding the fundamental forces in terms of, in this case for the molecules, it's important to do that so that then when you look at your data, you can interpret, oh, in this case I'm actually breaking hydrogen bonds or something, versus, oh, I'm pulling at enough force that I'm breaking a covalent interaction. So before we get that, this is an actual experiment from, oh, dang it, I had a reference that it should be right here on the slide, but it's from a paper. Not my data, somebody else's data. So this is how they did the experiment. That's the schematic. They had an AFM tip, they had an ethylene glycol linker, and then they had this protein that they were interested in. So this protein is a protein from tuberculosis bacteria. It's called heparin-binding hemagglutinin adhesion, so HPHA, and it binds, as its name implies, to heparin. Heparin is a glycosaminoglycan type molecule found in your body, in blood, all sorts of places, on surfaces, right, heparin. And so what this does is it helps the bacteria stick to you. So the point of this experiment was to try to understand how well this interaction occurs. And then I think later in the paper they actually were looking at variants of different types of these bacteria and how the protein changes, and if that changed, how well they stuck to stuff. So this is their experiment. And then this is the data, and here's some example curves they got from the data. So here, if you look at this particular curve, they didn't have any adhesion on that try. And here they have a small adhesion, which corresponds to kind of this peak. And then this is one where they have a bigger adhesion, which corresponds to this peak. So they did this a lot of times, I don't remember how many times exactly, and they got this histogram, which showed, so 6% of the time they got no adhesion, and what is that, 5% of the time they got like 50 piconewtons of force. And so you get these kind of Gaussian distributions. So a couple questions about the experiment. The first one is logistics of the experiment. Why do you think they put this linker thing here instead of just attaching the protein straight to the tip? Why would I put this extra chemistry step, which again, as an electrical engineer, I avoid extra chemistry steps because I'm not good at chemistry. So, but in this case, they put this ethylene glycol linker, and then they put the protein. So,
Very to avoid things.
yes, right. So we talked about it yesterday. It's so you avoid the steric interaction between the protein and the tip, right? You put this basically a long string, and then you have the protein at the end of the string. And so the protein's not interacting with the tip surface, it's like flying away from the tip. So now when you actually bring it towards the surface that has heparin, it's going to interact with the heparin and not the tip. Okay? So that was why they did that linker. Okay, so here one of the things they noticed is they got these two different peaks. So there's sometimes you get a 50 nanonewton, a piconewton force kind of interaction, and sometimes you get something that's more like 100-ish piconewtons of force. So the question is, why do you think there might be two peaks in the data? So it's this protein interacting with heparin. There aren't two binding sites, but that's kind of the answer. In this case, what they thought was that there was more than one. So this is like a schematic. When they actually do the chemistry, the tip itself has actually got lots of these all over the place. It's a very sharp tip, so there aren't that many right at the tip. But every once in a while, two proteins interact. So when it pulls, you get twice the amount of force. That's why you have 2 peaks. But yeah, so you could, certain proteins, though, that is a thing that happens, is if you have 2 different binding sites, you'll come down, and it might, same thing, it'll have a bimodal or sometimes 3, because sometimes it'll bind one, the other, or both. Okay, so this is their experiment. In the paper, they wanted to make sure that the binding they were measuring was actually due to this protein binding to heparin. So there's many ways of doing this, but how would you design a control experiment where you would compare the data you got in this control experiment and this experiment, and then I could safely conclude that these forces were due to HBHA binding to heparin. So that's a little bit more of a thought experiment.
Using the same technique or some other technique like SPR?
Well, actually, yeah, you could do other techniques, but what would you do with the same technique, just as a sanity check?
You have a solution without the microbiome.
Yeah, so you can do the same experiment on the same surface, but without the protein on the tip. And similarly, you can do the same experiment with this tip and no heparin on the surface. And that's what they did in the paper. If you want to get fancy, another experiment that you could do that would involve not pulling everything out, you do your experiment like this, you get your data, then what you can do is actually flow antibodies or other things that would block either the active site or the heparin, because those are known. And then you do the same experiment on that, in that sample. So the advantage of doing something like that is you don't have to take everything apart. All you're doing is changing the media, right? You're putting in a new protein. In this case, they had different samples, but for certain molecules, you could do that. But yeah, so does that make sense? So this is a very kind of classic trying to understand binding interactions of different proteins. I pointed this one out because it was really interesting because they were looking at pathogenic bacteria cell and the proteins from it. So you could look at different strains of different bacteria. They have different ways of attaching. Or same for viruses, right? Viruses, different strains of viruses have better or worse efficiency at initially grabbing onto cells or matrix or whatever. So those are protein, like once they've stuck and you told them how those interactions occur. But how do they get stuck in the first place? So there's lots of small forces that occur as you bring things together. If you bring any molecule together, any surfaces together, you'll get forces. The smallest force, and the first one we'll talk about, is van der Waals interactions. If they have charge, you could get electrostatic interactions. Again, if it's like a long-range polymer or something, at some point you're going to be bending on it, so you have steric interactions, usually with steric repulsion, right? Because the molecule's going to push because it doesn't want to be compressed. And then one of the ones that is very dependent on the media and the thing you're looking at and is less well characterized in the literature is things they call, a lot of times they're called structural interactions. And that's what this picture is. Maybe I have a protein and the protein is, let's say, really hydrophobic, and I have it, somehow I managed, I don't know how, but somehow I managed to dissolve it in an aqueous solution. So in order to dissolve something very hydrophobic in an aqueous solution, what's something that gets typically done? Yes, so you add a surfactant, right? Or if you're cooking, if you've ever made mayonnaise, right? You take your oil and your vinegar, you mix it really fast and they separate, but if you add egg, right, it'll stabilize the emulsion. So if you put in a surfactant, that will stabilize the interaction. And so you'll have like a layer of not attached other proteins structurally around. Even without a secondary carrier, you can get these kind of structural interactions in water because certain proteins and certain molecules will have properties that arrange the water molecules around them. So if they're very hydrophilic, the molecules of water right around the surface will actually arrange in kind of sort of like a corona around them. So if two of them come in contact with each other, even before they touch, their layers of hydrated water molecules that follow them around are going to come in contact. And so you get some forces from that. There are some models for those kinds of things, but typically what happens in data when you have something like that is people model these other interactions, and then if there's a lot of other forces left over, they're attributed to a structural kind of interaction. And then you can look into different models if it's something like a hydration shell or whatever, but most of the time that's how it's done. It's like everything that's left over must be due to some kind of structural interaction. Now, if you have something that is slightly hydrophobic, just straight in water, the structural kind of interaction that you get is that water gets excluded from, like, water will try to stay away from the molecule, and so if another one comes in, they'll stick because both of them want to be stuck together with water away from them. So, eventually, as I think I mentioned before, if I push things close enough together, they will always stick. If anyone in here ever does anything with making nanoparticles or things like that, the hardest part of making nanoparticles is having the nanoparticles not stick all together. If you're making protein solutions, same thing, they'll eventually all stick. So eventually, if I put in, if I push things close enough together, they stick. So why do they stick? If you put things close enough together, you get what's called van der Waals interaction forces. And no matter what it is that you're pushing together, these will occur and these will be attracted. So I could take two helium atoms, push them, or helium atoms, push them together, and even though those are uncharged, all their valences are all happy, they will stick. And the reason for that is that there's something called London dispersion forces. And this happens because the cloud of electrons around your atom, in a textbook we draw it kind of uniformly around the atom, but if you think about it probabilistically, it's not always uniform. And so sometimes the atoms are a little bit more on this side, and as soon as they do that and another atom is over here, it will stick, right? So that always happens. So those are induced dipole type interactions. There's actual dipole interactions that also cause van der Waals. And then depending on the literature and who you talk to, sometimes hydrogen bonding gets included in what people call van der Waals forces. That depends on like the paper and things like that, but they'll usually tell you if that's what they're doing. So the reason I have a gecko picture is van der Waals interactions is why geckos can climb up walls and on the ceiling. And we'll talk about why that is. And if we could replicate this, we could all be Spider-Man and walk on the ceiling. So the incredible thing with that is that van der Waals forces are relatively weak. If you talk to physicists, it's a very weak interaction force. And they're much orders of magnitude weaker than something like an ionic bond even. Also, it's a short range interaction. You have to push the atoms close together for it to happen, because van der Waals interactions between atoms drop off by the distance to the 6th power. So you have to get really close for anything to actually happen. As I mentioned, depending on the paper, they include a lot of different subclasses. In this class, we'll talk a little bit about London dispersion forces, because that's the one that happens with everything. The key with van der Waals forces and why they matter, besides the fact that they're always there, is that between individual atoms, it's a very weak force, and it drops off as r to the distance to the 6th. But if you have many atoms, it's additive. And so you can actually generate significant force with van der Waals interaction. And that's how geckos work. So if you look at a gecko feet, it has these little hairs, and the hairs themselves split into even smaller hairs, and so forth. And each of those hairs can then, when it gets on a surface, intimately make contact with the surface and actually have a van der Waals interaction occur, and then they add up, and together they can sustain the weight of the gecko. So just some math to show you that that's true. So if you're modeling van der Waals interactions in your system, it's usually done with a power law, and you define what's called a Hamburger constant. So the Hamburger constant is used to represent particle-particle pair interactions. So if you can look up in a table what the Hamburger constant is for different types of pairs of atoms, or in material interactions. So it's a power law. As I said, for London dispersive forces, it's n to the 6th. And so if I do one atom or one molecule, and I have the pairwise interaction with a planar surface, you can see that although one atom versus one atom goes by r to the 6th, if I add up all of those, it'll go by r, or distance to the 3rd, right? Because I have so many at the bottom. When they add up, they actually generate a lot of them. So just so you have it, this is having done that integration in different geometries So you can look it up. And W is the energy. So if I want to calculate the force, I'm going to take the derivative of the energy. So if I do that, you can see in an AFM type experiment, typically we have like a sphere, like a tip, and a plane on my surface. And so if you do that math, you'll get forces that decay as 1 over the distance squared. So suddenly, yes, it's a short range interaction, but it's not that short, right? And in terms of the things we're measuring things on the nanometer scale. So van der Waals interactions happen like 5 nanometers or so away from the surface, or even sometimes a little more. And that's very measurable on an AFM. If you look at AFM data, a lot of times you bring the tip in, and then when you get close to the surface, you'll get what's called a jump to contact, and your cantilever will suddenly, like you're coming in, and then the cantilever will suddenly go whoop, and stick, and that's due to van der Waals interactions. If you do that, and that happens, it's very convenient for AFM measurements because, as we talked about yesterday, AFM measurements don't actually measure directly the tip sample distance. We have to like back calculate and then kind of offset where we think the surface is. And so if you do have a jump to contact point, it's nice because I know it jumps, here I'm in contact. Right? I know that that's 0. The other thing to keep in mind about van der Waals forces is they tend not to be dependent on temperature. So if you're doing an experiment with different temperatures and different conditions of solutions and things like that, van der Waals forces tend to be constant throughout the experiment. So it's a nice internal check, right? So you're changing the outside solution, you're changing the temperature, but when you get close enough, that interaction of whatever protein you're interested in the surface, that interaction is the same. And so you can always look at it. Oh yeah, I wanted to put a video. I don't know if we have it connected to the internet. We'll try. If not, just to start before the video, this is an example of the gecko and its feet. So, are there geckos in India? I don't know. Maybe yes. Those lizards that like dramatic reenactment. And so, if you look at their feet like web out, and then from there they have extra. It looks like extra toes, and then if you zoom in, it looks like little furry toes. And then if you go and use electron microscopy, that's the structure of those furry things, and that's kind of what you feel. If you zoom in even closer, each individual hair gets split multiple times, and then at the end, they're split into what's called CT. They'll explain it in the video. And it has like a little nubby part at the end. This is 500 nanometers, so this is maybe 100 nanometers in size. So the reason for that is surfaces are not exactly smooth, right? Natural surfaces. And so if you had like just a flat surface and you tried to put your hand on the flat surface, you actually don't get contact. Like my hand, obviously, when I put it on the blackboard, doesn't make full contact. So by putting all these little hairs in there, the gecko always ensures that there's full contact of the pad of the foot to the surface. And so in a way, it increases the surface area of contact by multiple orders of magnitude. And then, I don't know if the video is working. This is like the TED Talk where they explain gecko adhesion, and we'll talk a little bit about their explanation. Because I think it's interesting. It's a TED Talk kind of video, so it's for the general public. So you'll hear the explanation of how they explain this interaction, and we'll talk about it a little bit. doesn't happen.
And the word choice is bland.
Okay, that's good.
Grammarly's cutting-edge technology helps you craft compelling. It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity, scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spiderwebs. Instead, they take advantage of a simple principle, that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces. They're not as strong as the interactions between charged particles, but if you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do, stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness. But a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So the gecko peels up its toes and the chase is back on.
I like that video because it's cute. So, as you saw, right, they explain kind of where van der Waal interactions came from. So one of the things that the only thing that I think is a little bit oversimplified in that video is videos, they talk a lot about charge, right? And then they kind of backtrack and say, okay, but the gecko's feet and the surfaces aren't charged. So what they really are talking about is this induced dipole, right? So it's the fact that any molecule, if you wait long enough, the electron clouds are not going to be evenly distributed, so it'll have a dipole for a little bit. It'll have a positive side and a negative side, and then as soon as that happens, another molecule nearby with similar kind of characteristics will pull on. So that's my only thing in that video is I think it tends to simplify it too much to charge-charge interaction, which isn't exactly what happens. Now, saying that all the forces are due to van der Waals is also maybe a little bit of an oversimplification. They've done a lot of studies using AFM, very high precision force sensors. There's a lot of electron microscopy imaging to try to understand how that interaction occurs, all sorts of things. And they found that, as expected, van der Waals interactions always are there. So the gecko has to use van der Waals interactions because at least some of the time, because it can't, let's say it's using some kind of like static electricity, which it does on certain surfaces. So on certain surfaces, it's like when you rub your feet in your hair, so you get static charge buildup, and that's what helps it stick because that's a stronger interaction. But that doesn't always work. And particularly if it's raining outside and everything's wet, and you have very kind of rough, these kinds of surfaces, not something like glass. Static buildup of charge isn't going to help you on those surfaces. So that's why it uses van der Waals. The other thing that's interesting in that video, initially when they figured this out, they were super excited and they're like, hey, it's using van der Waals interaction to stick, and it can stick really hard. So as was mentioned, they have 2 billion, something like that, hairs on the ends. I think depending on the species of gecko and which surface it's on, you can actually have a gecko hanging upside down that can carry a 50-pound backpack. So it's like, half a person or maybe a third of a person, so that's a lot of force. And so they were excited, and then they realized, but how the heck does the gecko then unstick, right? So they have been able to make surfaces that try to mimic this. So we have made surfaces with kind of very long, thin protrusions. But the problem they were having is when you put them on a surface, they stick, but how do you take them off? And the solution the gecko has, and what most of these adhesives do, is you peel them off. So the adhesive interaction, right, with this little end thing is very strong. Like if it's like this, it's very strong in this direction. If I start peeling this way, right, I suddenly am having like a small amount of contact area unpeeling at a time. And so now I'm not generating as much force, and so you can actually peel it off. So it's very important for the gecko to always maintain the orientation of the hairs so that it can stick, otherwise it'll fall off. So this principle actually has made it into lots of commercially available things. I think it's Johnson & Johnson makes bandages that are like ouchless bandages. If you've ever, when you cut yourself, are they called bandages or plasters here? Okay. So those, when you put the kind where the adhesive doesn't hurt when you rip it off, the reason it doesn't hurt is they kind of dock the surface with the adhesive with this kind of texture. So it sticks really well. It sticks really well even if you get them wet. But then when you peel them off, as you're peeling, you're not generating a lot of force as you're peeling. If you try to like straight up pull it, it's a lot of force. If you peel the edge up, you don't have to use a lot of force. As was mentioned in the video, there's a lot of development onto using it for applications of trying to be Spider-Man and climbing up walls. There's a group at Stanford. The guy likes to call himself Gecko Man. He's weird. But he made these kind of pads that you can use to climb very slick surfaces. They are nowhere near as finely engineered and so small. They're actually, almost millimeter-sized pads. So it works when he's climbing on glass surfaces, because glass is nice and flat. But the cool thing with his pads is it has when you put them down, they're flat, and then as you're trying to pull your arm up, it will change the angle so they'll unhook. So anyway, that's geckos. As I said, there's a lot of work in that space to make engineered materials that use this principle. But besides that, again, every experiment is always going to have these forces. So that's something you have to keep in mind when you're doing these kinds of studies. If you come close enough together, you'll always have van der Waal interactions. I think we have a break. Yeah. Okay. I was gonna. Yes. Yeah.
Is it special characteristics of only geckos or is it present in all other?
No. So that is very much a gecko mechanism. Other lizards, for instance, don't have that. So other lizards, to climb up walls, use claws, basically, to climb up the walls. Certain spiders and insects use that same principle. It's less impressive because they're a lot lighter weight, so they don't have to engineer it quite to the extent that geckos have to get really so many hairs on the end so that they can generate enough force to support their weight. If you look at a spider, it has a lot of furry protrusions on the end of its feet, but it doesn't need to have as many because it's smaller. But same principle. Other animals don't. So like a octopus, right, uses suction and stuff like that. So there's different mechanisms for that. Are there questions on van der Waals?
Maybe continuation with her question. There is an insect is there. If you come to our
Sorry,
body.
can people be quiet for a second so I can hear the question?
So continuation with her question. There is an insect which come to my body that's soaking the blood.
Yeah.
When you take out that things, it is become very hard to take out the things. So what's the cause there?
Yeah. So like ticks.
The black color things. I don't know actually that the biological name.
That depends on the bug. So different bugs have different techniques. I know ticks because I had a friend who studied their sucking mechanism. It's it kind of looks like a micro scale needle, and it has ridges like a screw. So when the bug goes to land that the tick comes in to bite, it actually screws its proboscis into your arm, and so then when you try to pull, it's like barbed and it won't come out. So you have to turn the other direction to get it out. Certain other insects and animals have actual like barbs, so they're just meant to go in and not come out. There's a bunch of other designs. Actually, along those lines, it's totally an aside, but it's very cool. There's a guy at Clemson who studies them. If you've ever seen butterfly, right? Butterflies drink water from little drops or nectar and things with these long proboscis. And it's not like a straw. They don't actually use suction to get the liquid in. What it is a very well engineered, if you look at them, it kind of looks like this. And when they unfurl it, it goes on the surface with the liquid, and then it actually uses capillary action to get the liquid into the butterfly. So that way the butterfly doesn't have to have a mechanism to pull a pressure, it actually just uses capillary action to get liquid in. And so my colleague studies these, and they're actually building engineered versions to be able to sample very small volumes of liquid like eye drops and things like that that are hard to get much more easily. Because you don't have to generate a pressure, so you can just touch it onto your eye and it'll suck up a little bit of tears, and then you can do analysis on that. But the other way around, those bugs that bite and suck blood, people are also trying for microneedles to like inject drugs into people. They're making, same thing, like looking at biology and then trying to make engineered versions of those so that, you know, because they work so well. So, yeah.
When you discuss about the forces, you forget about the weight.
Sorry?
When you discuss about the manual forces of the
Yeah.
gecko, we forget about the weight. So when you implement that thing in our daily life, or that you gave example of that making the something. So what about weight then? Will it not impact any weight on that forces?
Oh, the weight, like gravity.
Yeah.
So that's actually a good question. So gravity for, I mean, they're all good questions. But gravity, for most of these things, we don't have to think about gravity at the nanoscale, because most things are so small that the force of gravity is insignificant. Now, the gecko, that's the impressive thing, is that obviously, like, the force of gravity on, you know, van der Waals with one of these, pulling with gravity on a force of a gecko, it won't stick. But if you add up all those forces, you can have a counterbalance of very significant force, which is, in this case, the gravity of a gecko pulling. In cell-based experiments, sometimes we do have to take gravity into account because cells do have enough of a mass to, you know, settle in solution, but typically that's just we're waiting until they settle kind of force, so we don't typically have to think about it too much. It's in solution, so buoyancy and things also take into account. You do have to take into account fluid, shear, and viscous drag, those kinds of things in those systems though. But yeah, if you're like nanoscale, really nanoscale, gravity doesn't matter so much.
So if gravity is not matter, if you take bubbles are going up in the water.
Yeah.
So can you make some mechanism that if gravity is not matter in the water, bubbles or water?
Well, so, yeah. But if it's a nanoscale bubble, though, right, that's a buoyancy thing. So, I mean, so same thing as what we were talking at the beginning. There's actually a lot of work on how to stabilize bubbles so that they don't all clump together and they don't all go up. That actually is what they do to make ultrasound contrast agent. So if you know, there's MRI and CT and X-ray and there's contrast agent for those. If you go get ultrasound, contrast agents for ultrasound basically are little tiny mini gas bubbles. Gas bounces back. So there's a lot of work on how to stabilize those because you can't just inject a person with air. So the very initial one is very interesting. What they did is they would take albumin and then they would shake up albumin. And again, albumin is the same as egg whites. So if you've ever seen egg whites, if you shake them up enough, it makes lots of bubbles and foam and they stay. And that's what they used to use for the first ultrasound contrast agents. We've gotten better at it, so it's a little bit more complex than just albumin bubbles now. But it's the same principle. It's just an air bubble that is decorated with things or covered in things so that it's more stable and doesn't stick to each other. Well, okay, well, we're not breaking, we're going. Okay. So the other force I wanted to talk about, well, yeah, I think we have time for a bit of a break. We're going for an hour. Yeah, just so people can move around. Because then there's lots of equations, and I don't want to show all the equations where people are sleeping. Okay. I think we'll get started again. So the other force I want to talk about is electrostatic interactions. And that is actual charge-charge interactions. So as opposed to van der Waals interactions, which are charge independent, right? They occur whether or not you have charge, and they happen because of kind of molecules and atoms having dipoles forming. So this is actually charges interacting. So from basic physics, right, you know positive and negative charges attract. Now, in a physiological condition, it's more complicated than your physics textbook. And the reason is, we are bags of salt, right? We are full of salt, and so we have lots of salt ions floating in solution. So if I had like a charged protein surface or whatever coming into contact with another surface over here, all these ions in the middle get in the way and change the interaction. So just in terms of how salty are we, so if you think about water and the ionic strength of water, you might think, well, water doesn't, if pure water, deionized water, doesn't have any salt in it, so it should have some kind of zero ionic strength. But as we know, it has a pH, right? So if water is at pH 7, that's its ionic strength. It has ions at 10 to the minus 7. Now, if I keep adding salt, we sit at 0.15 molar salt. I don't know, people have done experiments or things. If you've ever used phosphate buffered saline, PBS, or cell media, right? All that is at 0.15 molar. Has anyone actually tasted buffer? Like tried it to see? No? Okay, I did once. It's really salty. It's not the ocean, but it's like, you know when you're making spaghetti and you add salt and then it tastes really salty? That's what it tastes like. So yeah, don't try drinking things in lab. This is an experience. Actually, for anyone who has contact lenses, saline solution for contact lenses and salt eye drops, those are at 0.15. So if you've ever accidentally gotten some of that in your mouth, you know how salty it is. So all those salt ions in solution will shield some of the charges interacting. Because you've got, let's say, sodium chloride, you have positive sodium, negative chloride ions, and they'll distribute away from the charged surface. So if you have a negatively charged surface, the sodium ions will want to go towards the negatively charged surface, and the chloride ions will want to go away from the negatively charged surface. So why do we have charged surfaces in biology, or charges? We talked about this a little bit. We have all sorts of ionizable or dissociable groups, including strong and weak acids and bases, right? So if you have a protein or something like that, and it has carboxyl groups at the right pH, right? You get, some of them are going to be COOH and they're not charged, but some of them, the hydrogen is going to pop off and they'll have COO minus, and then this is now an ion free to go floating around in solution. In addition, what does happen with especially material surfaces is you can actually have ions get stuck on the surfaces, so you can get charge buildup because you have, usually it's multivalent ions, they're big, they'll attract and they'll actually stay stuck on the surface, and they will produce a charged layer. So it's like static electricity. When we use this, you get charge buildup. Same thing happens in the body. As a first pass, today we're just going to talk about this kind of surface because that's easier to think about. So you can get, you have weak acids or bases, and they are dependent on pH. So it's important in your experiment to know what the pH is, because whether or not a surface is charged, whether or not your protein is charged, whether or not the cell feels any charge, it has to do with pH when you're talking about these groups. Certain groups, right, strong acids, are so strong it doesn't matter whether you have whatever pH, you have to go to really, really crazy pHs before they are not deprotonate. So sulfate groups in solution in the body are always negatively charged. So just so you have them, you may have memorized these things in biochemistry class. I don't know, maybe, yeah. I'm an engineer, I don't memorize these things. I memorize them for a test and then I look them up on Wikipedia. So here you have some right there. So those are all the different types of groups that you will typically run into when you're looking at biological relevant molecules that have charge. And here's the range of their pKa's. So if you look at let's say if we were looking at carboxyl groups, right, you have to, they have a pKa around 3. So if you're too acidic, you'll be back over here. If you're too basic, it goes down the other way. So each of them has a different pKa value. One of the interesting things is we think about terminal mean type groups being having charge, but their pKa is right around 8, so it's actually kind of in balance. Same with histidine. Histidine is right around the pH of 7, right, 6.5. So if you're thinking about histidine residues, like half of them are going to be charged and half of them aren't. So I've zoomed in, say I have two proteins interacting, and they have, or two surfaces, and there's some negatively charged layer. What happens? So what you end up having is initially, right, you have the charges, and then some of the opposite ions are stuck on the surface. Ions are not points, right? They're not electrons, they're not tiny. They take up space. And so right up against the surface, you'll have what's called the Stern layer. And it's a few angstroms, but it's where the size of ions matter. Now, for most things, a few angstroms, for most of your experiments, we're talking nano, so angstroms is smaller than nano. For most of those, it doesn't matter too much for modeling. That changes if you end up using very large multivalent ions, because they're actually relatively big, and so it can extend out a little bit, and you actually do have to take it into account. So, if you go far enough away from my surface, and I just have salt, like if I put sodium chloride in water, and I pick up a bit of the water, what's the net charge in the water? 0, right? Because sodium, chloride, they match. So that's electron neutrality. So now if I have my surface and I put it in there, or my protein and I put it in there, I still have to hold electron neutrality. So I have the salt ions that are in solution, and I have the charges from my protein and the groups that dissociate from them. So if I have a negative surface, then in the bulk, it has all the ions plus the groups that are dissociating, the positive ions that are dissociating from my surface. So when you look at electrostatic measurements and measurement of charged proteins and polymers and things, which a lot of we are a mess of charged proteins. There's what's called the diffuse layer. You also hear it called double layer, diffuse double layer. They use different terminology. But so right up to the surface, you have the Stern layer. That's where the ions are kind of stuck. And if you go away from that surface here, right in this region, I actually end up having more ions that more counter ions, more ions of the opposite charge from my surface than co-ions. So my net charge in any one of these sections is not zero because it's balancing this big thing that can't move around. Now if I go far enough away, I'm back in bulk, and then in the bulk section, the positive ions and the negative ions add up, right? So this is the layer we're interested in, is the diffuse layer, because if I have two surfaces interacting, that's kind of the layer when they come together, that's when they start interacting with each other. Now, the crazy part, as an experimental person, having done experiments, is depending on the salt concentration or the ionic strength of your buffer, this diffuse layer can actually extend quite far away from your surface. And so you might have things interacting on the order of like 100 nanometers away from the surface, which again, when we're talking nanoscale, it seems small. But if you think about the size of a protein and the size of a cell, 100 nanometers is actually kind of significant. So generally speaking, we can simplify electrostatic interactions as exponential decay. So the concentration of my ions, the potential energy away from the surface is going to decay with an exponential. This exponential, so d is the distance away from my surface. This kappa, 1 over kappa, is what's called the electrical Debye length, Debye-Huckel length, Debye length. It's the characteristic decay length of interaction for electrostatic interactions. And so it, depending on your ionic strength, is going to be bigger or smaller. But you can think about things as decaying as exponentials. So back of the envelope, if I'm more than 5 or maybe 10 Debye lengths away from my surface, I don't feel any electrostatic interaction. And then if I'm less than that, is when exponential starts increasing up and I'll start feeling forces. This is just to point out, like again, in the bulk, if I'm in the middle, there's no charge. And then as I come close to the surface, I get more counter ions because I have this like negative charge right there. So back to basic, what is it? Electricity and magnetism physics 2. I don't know. If you remember Poisson's equation, yeah, right. The second derivative of the electrical potential is proportional to the charge. So it's like if I take a volume and I look at the electrical potential, the charge is inside, right? That's all proportional. Is that people remembering? Okay, good. So in the solution, the charge is going to be rho, which is like the density, yeah? It's the density of ions. And then the number density of ions, if I have, I don't know, I'm making up a number, 0.01 molar, right, of ions in solution, that's rho. But I want to convert it to charge. So I'm going to multiply by the valency. So if it's sodium, it's 1. If it's calcium, it's 2, right? Because every ion in calcium has actually 2, is a charge 2. And then you want to multiply by E, which is the charge of an electron. So that's here. And so that top term is the charge density, because it's the number density times converting it to charge. On the bottom is the permittivity of the media, which you have a number for the E naught, or epsilon naught is in air. And then in water, you have to add a relative permittivity term to adjust. And one thing to note is that this number does change with temperature. Not a huge amount, but if you're doing an experiment, less for very biological things, because we tend to stay at 37, and even the difference between 20 and 37 is not so big. But if you start talking about when they are engineering surfaces and they're looking at things for more commercial scale applications, this actually matters. Okay, so how is the density of ions determined, right? So if I know my density of ions, then I can calculate all this. So the density of ions at equilibrium is defined using what's called a Boltzmann distribution. So it's the density in the bulk. So if I have 0.1 molar sodium chloride, I have 0.1 molar sodium ions. Time an exponential, which depends on the electrical potential. That's on the electric field. And why is that? Well, if I have an electric field, my ion is going to move in the electric field. So that's the Boltzmann distribution. So if you put it all together, you end up with what's called the Clausius-Boltzmann equation, which gives you in one dimension, the second derivative of the electrical potential is going to be equal to a term having to do with the media permittivity, and then a sum of all the charges in my solution, so all the ions together. So I'm going to skip this, get to the picture. There's the picture. So the equations are in your notes, but we'll look at it in the picture. So what does that mean? That means you end up with these kinds of distributions of ion charges away from my surface. And if you actually have to do measurements and do modeling to actually get numbers out, the thing that's important to remember is if I have surfaces coming together, there's always some kind of mid-plane which has symmetry, which will make the math easier. So don't do more work than you need to. The concentration of the counterions on the surface ends up depending on the surface charge density of my surface or protein or whatever, and the ion concentration at the midplane. So when I have my surface away from anything, it's at bulk. But if I have two surfaces coming together, the concentration actually ends up building up. So I have to look at the midplane of the two surfaces. So this is some definition, but the reason it gets called the electrical double layer is from a modeling point of view, this very diffuse distribution of charges away from your surface can be modeled as, see, I'm an electrical engineer, as a capacitor, two plates, and the second plate of your capacitor sits at a distance away from the surface that's equivalent to the divider. So it's called a double layer because you can model it as a surface with somehow a layer of matching counterions away from the surface moving together. But you have to keep in mind that while computationally or not mathematically it ends up being the same, physically what it is a whole bunch of ions. So if you do that and you do some math, and I did a lot of this for my master's thesis, so I got very good at doing hyperbolic signs. If you actually do in one dimension in a salt that's a monovalent salt, so something like sodium chloride, you can actually get a closed form solution and solve it. However, for anything else, this is a nonlinear second order differential equation. So you don't. So for any other geometry, you typically will have to compute it computationally. So this is a fun time. This is when I feel old. Back in my day, I had to write a computational solver to solve this for different geometries of the proteins I was interested in. Nowadays, you can actually get packages that do it for you. So my first name is Delphine. This is Delphi. One of the common packages you can get is called Delphi. I did not write Delphi. I remember when it came out because it came out like 3 years after I got my PhD, and it was like, oh, it would have been so much less work if I had this package. So it will actually solve it for you in a variety of geometries, particularly if you have complex proteins or larger scale things. So if you're looking at an implant surface and it's rough, all those things, don't give yourself the headache, just use one of the computational packages. This is the simple version. It ends up being a hyperbolic sine, and a hyperbolic sine is this function. But the easiest approximation, though, if you don't want to do all the math, is again, let's pretend we're in a monovalent salt solution. Are we usually, in biology, in a monovalent salt solution? No, right? Even if you think of PBS, phosphate buffered saline, PBS has sodium chloride, that's monovalent, but it has phosphate. Phosphate ions aren't monovalent. But for our first approximation, we're just going to forget calcium, all those things. They make things harder. We're just going to pretend everything's sodium chloride. And we're going to assume everything is going to decay with an exponential. And if you do that, you will get these forms of solutions. So what that tells you is the electrical potential away from the surface is equal to the potential at the surface times an exponential which decays with the Debye length. And the Debye length depends on the ion concentration. So in the Debye length, this is my salt concentration. So for biology, this is 0. What is it? What's this ion? Like, what's the ionic strength of PBS or and media? 0.15, right? So this is 0.15 molar. This is Faraday's constant, which is converting the concentration into charge. So Faraday's constant is the amount of coulombs in 1 mole of electrons. So Faraday's constant times concentration will give you charge. This is the media permittivity, and then this is gas constant, and that's the temperature. So things depend on temperature also, right? But this is an easy to calculate value. At 0.15 molar at roughly physiological condition, the Debye length is roughly 1 nanometer. So if I look at the electrical potential away from my surface, in physiological condition, it decays with a characteristic length of about 1 nanometer. Now, if I look at it in 0.01 molar, so I take out some of the salt, it will decay with a Debye length of 3 nanometers. 0.001 molar is 10 nanometers. So if you're in 0.01 molar salt, you have to go, it will go out to like 100 nanometers before it gets near 0. So it's very significant, of course. Now, this is 2 different approximations. One is a constant potential application, which for biological samples doesn't usually hold true, but for engineered surfaces sometimes does. So we talked about STM and things like that before. So if you actually physically are putting an electrical potential between your tip and your sample and you're measuring, the system is going to keep the electrical potential at the surface constant, and you would use this formulation. For most biological things, that's not what we do. What we do is measure forces and then back calculate what the surface charge density is. And again, the surface charge density depends on how many carboxyl sulfate, all those groups you have on the surface. So again, physiological conditions, it's near 1 nanometer. It's like 10 nanometer at 0.01. I mean, if you go to 0.001, it's 30 nanometers. To note, if you add more salt, you calculate a Debye length of 3 angstroms. That makes no physical sense because 0.3 nanometers. If you're within 0.3 nanometers, like ions have the volume. So what that tells you is basically if I put enough salt in, if I go up to 1 molar salt or something like that, I've put enough ions in there that I basically completely shield out electrostatic interactions. So for most experiments, when you're trying to look at how the charges interact and whether, like for the gecko for instance, is charge interaction important for the gecko to stick, you can do the experiment and then keep adding salt and see if the forces change. And then if you add enough salt, you know you've added enough salt that there's no electrostatic in your experiment. Meanwhile, the van der Waal interactions are going to stay the same. The other way to get around electrostatic interactions is to change the pH, right? So you can make the measurement, keep changing the pH, and then you get more or less charge because the pH changes in your solution. So that's the electrical potential, but how do we do force? Oh, sorry. Exactly what I just talked about. Oh. I'm missing a slide with the last most important equation. So you actually can take the electrical potential and convert that to a force. And the way you do it is calculate the electrical potential at the midpoint between the two surfaces that are coming together. So if they're far enough apart, this is going to be 0. And then as they come closer and closer together, the two exponentials are going to start to add up and you get an increase in potential. And then you're going to do a force balance. So the force on this surface, and then I'm going to draw a giant box. Goes all the way over there, right? And all the way over here, way over there in the wall, I'm at bulk conditions. So the electrical potential way over here is 0. And you're going to make a difference, and using that, you can calculate the force of the thing that's over here, right? Because you've made a force balance box. I will send you the slide that has that actual equation. But basically, it ends up being an exponential for that approximation. This is an example of actually why this matters. So, electrostatic interactions are probably the longest range you can have long-range steric interactions if you have really long polymers. They go out a long ways. But in terms of not contacting things and whatever, electrostatics are the things that will go the furthest. And a lot of proteins and things will interact with charges. And so you can get attractive or repulsive forces, and biology uses that to help with docking and things like that. Engineering-wise, it gets used, as I mentioned, I think yesterday, for colloidal stabilization. So if you're making nanoparticles, you want them to interact with certain things and not other things, you can add charge on them to have them do that. And if you do that, then all the particles are charged the same way, and so they will not want to get together, right? It'll keep them apart, and we won't have everything clumpy again. Now, the nice thing with biology, if we go back to wherever that table was that I should have memorized in school, but I didn't. Oh, there it is, right? We have all these groups. If you remember when I talked about spider silk, we know a lot of large assemblies of things from biology. We know what they're made of. We know the individual protein components. What we don't always know is exactly how those assemble into larger scale materials. And those assemblies are what give it its particular properties. So this is an example of a study we did on wool. Wool is, as you know, sheep hair. Right? So if you take images of your own hair, it looks very much like this. This is, except hopefully your hair is slightly thicker than this sheep hair. This particular wool comes from merino sheep. It's like expensive wool, which is why it's thinner, so it's nice and soft. But one of the things you'll notice is there are these scales on your hair. Sometimes in shampoo commercials, they will show these pictures and show like this is before the shampoo, and then after the shampoo it's even more smooth, right? So why do we care? Well, because the little hairs, that's how biologically that's how they grow. It's kind of like beta sheet assemblies that grow. And what happens with your hair when you get split ends, you know, the ends of your hair split, it's these little wool or hair scales pull up, and then the whole assembly unwinds. In wool, if you ever have like a sweater and you wash it in the washing machine at a hot temperature, and then you dry it at a hot temperature, what happens? It becomes rough and it becomes tiny, right? I am tall. This is a big problem for me. I buy these nice sweaters and then I forget and I put them in the laundry and then it's a problem. So why does that happen? Because at hot temperature, you have enough heat that the bonds that occur at the scale, it's made out of like a cuticle, kind of like your fingernail. And then there's a protein that keeps it tight. And if you put it in heat, you're going to break all those bonds, and so now all the scales flare out, which makes it rougher and makes all these separate wool hairs tangle. And so that's why it shrinks, is because the nice like straight fibers, they get all kinky, they get little scales and they all tangle up on each other, and that shrinks. So this was a study we actually did because a local fancy wool manufacturer was looking at how to make shrink-resistant wool. So if you go to fancy, what is it, like North Face, the people who make like to go climbing in mountains, fancy warm clothing. Wool is very nice because wool keeps you warm, but also is breathable. It's a natural fabric. So the problem with wool is it shrinks. North Face has a proprietary process to prevent shrinking. The easiest way to prevent shrinking is take your wool, put it in kind of an acid bath kind of thing that pretty much destroys most of the structure, and then backfill it with something like nylon. So what you end up with in that kind of scenario is it's no longer really wool. It's wool with, it's like a synthetic material. North Face's process doesn't do that, but it's proprietary, so we don't know what they do. And so they were looking for ways to figure out, we know the composition of wool and hair, but we don't know what's this stuff made out of that keeps the cuticles down. So what we ended up doing is a combination of things to identify the groups that were right at the edge, so that then you could come up with chemical treatments that would reform those bonds and keep things tight. So we used charged AFM tips. And so how do we make a charged AFM tip? So if you wanted to do one of these experiments, what you want is a known charge density on the tip. Because then you're coming towards something where you don't know the charge density. Here's my here's the equation with the exponential. I know if I knew the info about the tip, I know what my water is made out of, I know the salt concentration, I know the distance, so my only fitting parameter is the charge density on the wool. In order to make tips with known charge density, we used gold-coated cantilever tips. and we made self-assembled monolayers of using chemistry where you get thiols binding to the gold, and then you have something like 10 carbons, and then at the end you have a carboxyl group. When you do that, on top of gold, all the little carbons line up, so you get a very nice packing and a really nice uniform surface. And if you do one of these chemistries, every time you do it, it packs the same. So every time you do it, you get the same surface charge density on the tip. So you can do that with carboxyl groups, you can do that with amine groups, you can do it with sulfate groups. So for everyone here, if you're going to do experiments, those are very useful because they're very well uniform, very well characterized surfaces. As an aside, you can also actually do it with non-charged groups. So you can put a hydroxyl group, and now you have a neutral but hydrophilic surface, or you can put hydrocarbons, and you have a hydrophobic surface. So in this case, we had positive charged tips and negatively charged tips. We did a bunch of AFM force curves. So the interesting thing with these data is that this is one sample curve. This was done at 0.1 molar. So you can see it's an exponential, and you can see it comes out to roughly like 20 nanometers or so. So that makes sense, right? Because the characteristic length should be like 1-ish nanometer. So we fit our exponential to all these data, and we measured average surface charge density over a scale. So this is AFM imaging of like one of these regions right here. And then we, in the box, went and made lots of measurements and got a charge density. And then we correlated where the point was relative to the edge of the scale to look at the charge density as you get towards the end of the scale. And what we found was as you get towards the end of the scale, you get a lot of positive charge right at the end of the scale. So there's a bunch of amine groups right there. And then it gets to much more neutral when you move away. And then we confirmed that using electron microscopy. So I don't know if it shows up really well, but in this picture, we used nanoparticles that were targeting. They had a chemical on them, chemistry on them, so that they would bind to free amine groups. And then in electron microscopy, if I have gold in my sample, it turns really bright. And so that's what we did here. All the bright spots are gold. So we can see where all the amine groups are located. And so basically all the X is where they are. So what that told us was that all the charge groups are kind of where we want, like in the interesting area. And we want them to not be exposed. And so from that, a chemical engineering friend worked on different types of treatments that might kind of use up the three groups and keep everything down. So it's kind of, again, it's basic science, but for an application. So yeah, that's what I wanted to do with electrostatics, and I was going to stop here for small scale forces, and I was going to do a little bit of intro. For this afternoon, we have a lab with cells data. But are there questions on like kind of smaller scale forces and why we want to measure them before we move on? No, we're feeling good. So yeah.
From this electrical double A's, this shows the case of salt, where you have the equal dissociation cost. And in the case of suspension of molecules,
Yeah.
so like what kind of molecules are next one? Then one more thing, especially with the surface and molecular interaction. For example, if you're putting nanoparticles or something into that, you have many surfaces.
Yes, yeah.
So computationally also how to
Right. I'll start with the last one first. Actually, I was going to show the data that would have helped. Maybe I'll bring it tomorrow. One thing to keep in mind is surfaces aren't aren't that. They're not just one surface. Particularly in materials that are crystalline, you end up with crystallographic planes that have very different properties, particularly with charges. In a nanoparticle, this happens at the nanoscale. Depending on the size of the particle, you can get very different behaviors with just very small changes in particle size. So in those experiments, we've done kind of characteristics of bulk surfaces at the small scale, and then there's other characterization techniques for particles in solution that kind of give you like what is the net charge on a particle. So zeta potential is one of them. And we correlate that back to the experiments we got on surfaces to know kind of which surface the particle looks like. What was the first question? Yeah, so this is a simplified thing, right? I have my surface, I know the pH, I know what my salt concentration is. The human body is more complex than that. In particular, the biggest problem, but the biggest thing you have to take into account is if I have a lot of charge. So, I don't know if people are talking something. But if I have a lot of charge on a surface, on a molecule, the salt ions will redistribute, but H plus will also redistribute near there. And so you actually have a pH gradient that forms. This is especially true in cartilage tissue, because if you remember the molecules from yesterday, all those side chains were highly charged, and so what ends up happening is the pH inside your cartilage is closer to 5 compared to just outside because of the ions coming in. And so when you do that, then of course, if you look at the pK of different charge groups, you get much less of them protonated or deprotonated based on the pH locally. And so you have to take that into account. In these experiments, typically we don't, because that only happens when the two things are really close together. No, for this kind of stuff, we use just the exponential. Yeah. So for the experiments with a tip and a surface, or a tip and a protein, you tend to use this to back out certain numbers that then you can use in a package like DAY3 to look at how things orient, like even smaller scale. Like if you're looking at how docking of proteins and things may happen, it's useful to run that kind of simulation.
Basically, I'm doing docking only protein.
Yeah.
Yeah.
But in those cases, for those experiments, again, it's a scale thing. So you could do, if you're looking at protein-protein docking, as you're bringing the things together, these approximations work pretty well. Right when they're close together, that's when the approximations break down. But for most of the docking, you're interested in like, once they get close, then they dock, and then when you pull them apart, how much force is generated. So as a first approximation, these work pretty well. If you want more detail of like, what you don't get in these experiments is, I have a protein here, a protein on a surface, I can measure the forces, but I don't actually know the conformation and the orientation. And so then if you measure the forces, you get a feel for what they should be. You can run a program like Delphi or some of the other docking programs that will tell you how, or give you their guess on how docking occurs. There's a bunch of ways of doing that. You can do Monte Carlo simulations. And how that happens, then, you can compare to the experimental data. Like, does it make sense? A lot of times you end up with a couple different ways that it could happen in the simulation because they are energetically similar, but maybe the interaction force at the end wouldn't be. And so then you can look at the experiment and be like, no, it's weaker than this interaction, so it should be this one. Yeah. Any other questions?
Ma'am, there is a question. You Boltzmann distribution.
Yeah.
At equilibrium, mu1 b equal to mu1x.
What-
mu1 b equal to mu1x you give, and there is also you give in the box some other equation, and at any location another equation. There is another term. You can open this. Right?
Yeah.
I think 22. 22.
Yeah.
In that bulk at location, that last term.
Yeah.
Can I explain that?
Oh, that's a good question. So if you look at what the terms go into, so in bulk, right? You have the ion concentration, and then one of the forces acting on the ions is basically diffusion. So same thing. Near the surface, or when you're close enough to the surface that you feel the electric field, you get diffusion force happening. Right? This is just force due to the concentration packing of ions, and then you get electrical drift. So this is the electrical force on that ion because of its charge. So those are the two forces that are affecting the distribution of charges away from the surface.
When diffusion and drift both are there, letting at any location.
Right. So they're both in there, right? That's the diffusion or entropy term. This is the electrical term right there. So the sum of them together is what give you Boltzmann distribution. If you somehow could turn off like diffusion, right? What would happen is all the charges would pile up on the surface, and I just have exactly, the right number of positive and negative charge right on each other. But because of diffusive forces, I can't do that. That's a huge diffusion gradient, and so that's why you actually end up spreading out that amount of charge over a longer distance. Does that make sense?
So at equilibrium, that can I draw? Can you draw the diagram?
Yeah. So at equilibrium, that's where it looks like I think it's this. So at equilibrium, the distribution of charge away from the surface looks like an exponential decay, and then on another surface also looks like an exponential decay, and they kind of add up with each other. And when I say at equilibrium, that is how long it takes for this diffusive gradient to establish, and that is for the purposes of anything you're ever really interested in, almost instantaneous. If you're doing molecular dynamics simulation, it's not at equilibrium in those types of scenarios, but for anything you can measure, it's going to be at equilibrium. We don't have things that go into like less than nanosecond type of measurement technique. We don't have data acquisition at that rate.
So at equilibrium, how this diagram will draw? Arrangement of electrons for ion, positive ion and negative ion.
Oh, yeah. If you look at that one, this is me trying to draw by hand what that looks like. So it will look something like this, right? You in the middle, you have the same number of pluses and minuses, and then kind of in this layer, you have more pluses. You still have some co-ions, but you have more counter ions, and they distribute with these kind of exponential distributions. Yeah, I could put more ions in the drawing, but it takes forever to draw these stupid pictures. So, yeah. Is that clear? So if you're actually measuring small scale interaction forces, as I mentioned, van der Waals is always in there, and then electrostatics are usually the next one that everybody always models. Just for everyone's, if you're picking a paper that does any of this, they may call the combination of van der Waals and electrostatic together something called DLVO, Derjagen, Lando, Verve, and Overbeek. DLVO theory. So DLVO theory is just the van der Waals forces I showed with the power law plus the exponential version of electrostatic. So that's typically what everybody does. So that's what I wanted to do. Good? Okay, I'm going to go to the next one so we can be ready for our thing this afternoon. We can take like 5-minute stretch, do some jumping jacks. Okay, so this afternoon, we have some data, and we're going to look at, instead of molecular forces data, we'll look at indentation in cells. So shifting gear a little bit. And the data I have for you is actual data from an experiment where we were looking at vascular smooth muscle cells, and we had controlled cells, and then cells treated to keep them more muscly. So I wanted to do a little bit of background so that the data makes sense when we look at it. So vascular smooth muscle cells are the muscle cells on the outside of your arteries and your blood vessels. They help regulate blood pressure, right? They make the artery big or small. So they're similar to yesterday. When was the stomach? Yes, right. Smooth muscle also. So they're all a little bit different, but they have contractile type actin mechanisms. One of the problems with vascular smooth muscle cells, why we have atherosclerosis, which I hate pronouncing, but cardiovascular disease, it happens because something stresses the cells. And when vascular smooth muscle cells are stressed, they go from being your more textbook example of muscle cell, where it's like a spindle and it looks like all aligned and it's got muscle, and they start looking more fibroblastic, so they spread out, they migrate, they also put down collagen. So a little bit of that is fine, and all our cells are in a continuum between this kind of very proliferative synthetic phenotype where they're proliferating a lot, putting down lots of collagen, spreading out but not contracting, to a more quiescent contractile state. The problem that happens with disease and all sorts of things is they shift and more of your cells go into this very proliferative, not muscly state. And that's why you end up with problems in part in atherosclerosis, because you get all these muscle cells that kind of turn into fibroblasts and infiltrate into the blood vessel. They'll re-stenose arteries, all sorts of problems. So in this particular experiment, we had control cells, and in a petri dish, the cells are not in their happy state, right? Because you took them out of the blood vessel, so they're going to do what they do when they're under stress. They're going to spread out, and they're going to put down some matrix, and not act like muscle cells. So they're kind of like, in the control, they're kind of oversimplifying, saying they're in a disease state, but they're kind of there. And then we were giving them treatment using heparin-coated nanoparticles. So heparin is this molecule, natural molecule. It's an anticoagulant, but it also is known to help endothelial cell proliferation, but keep vascular cells, vascular smooth muscle cells more muscly. And so what we were interested in this experiment was to see if you give these treatments, the cells go back to being more stiff muscle-quiet cells. So that's the data you'll get. A couple things on the experiment. We did, let's see, I think I have a picture of what it is. What is the picture? Dang it. Oh, here we go. Yeah. So it very much looks like that. We had a spherical indenture, 5 microns. We pushed it to the cell. We went at 1 micron per second. It's a 5 micron diameter radius sphere, and the spring constant is 0.1 newtons per meter. So I think those are all parameters that are in your notes. So make sure you have your notes with you when we go to the lab, because you'll need these numbers. So what we're going to do in lab is take the raw data and convert it into indentation data. So convert the raw data from what the machine outputs to force versus indentation. So like the data from yesterday, you have to remember the AFM again does not measure tip sample distance. So you'll have to do, the Excel spreadsheet kind of walks you through some of that. So you have to take the piezo motion and the tip motion and add them together to know where the tip has moved. And then the big thing that's hard for indentation data is where is the contact point in my data. So you'll look at the data and as groups together come up with a strategy for figuring out where you put the contact point. Because the first thing that'll happen is you'll, oh, that's weird. You just walk, oh, I went the wrong way. Walk the wrong way. Let's go back to data. Okay, no. Okay, so where, like, you'll get the data, it'll finally be converted, but this scale, you won't know where the 0 point is, right? So you'll need to figure out where to offset your experiment so that you decide where that point is. So there's a couple, we talked a little bit about strategies for figuring that out. So one of them is looking at away from the cell, how much noise I have, and if force starts increasing above the level of noise, then that's where I'm going to put my contact point. That's not too bad to do in Excel, right? You can scroll in the data, kind of look and see. If you want to get a little fancier, which is a little more difficult to do in Excel, but not too bad to do in MATLAB if you're used to MATLAB, you can actually fit, take parts of the data and fit it to kind of 2 regimes. So if you fit it to a little bit of an exponential, and when do you get a good fit? That's the point of inflection, right, where the data comes up. So that's another way to do it. The last way to do it is similar. I'm going to assume that initially, when I indent the data, at the very beginning, the data is going to look elastic, and I'm going to fit an elastic model, and I'm going to find the contact point by finding where you get invested. So don't pick as a group. There's other ways of doing it. I mean, maybe you zoom in and you eyeball. I don't know. You'll all look at the data and determine where that contact point is. So once we do that, we're all going to talk about it together, because this is one of the problems, I think, not problems, but one of the known issues in literature is that while things have gotten a little bit more standardized, instruments now come with algorithms built into them to kind of guess and give you an estimated contact point. Different manufacturers use different algorithms for picking the contact point. So it's important to know what you're doing when you have your own data so you can report it. So again, someone can compare apples and apples, because what you hopefully shall see in lab is picking the contact point makes a huge difference in terms of what modulus I end up getting. Because if I pick my contact point, here's some data. Actually, here's data where they haven't set the contact point yet. Like if you look at that A curve, right, and you look and you're like, well, force starts increasing over here, and I put the contact point here, or I can like wait until it's like pretty significant and put it here. That's like almost 500 nanometers, almost a micron of difference in depth. And when I fit my model to get a modulus, that'll make a huge difference in the number I get. So that's the other thing we're going to do on the second half, is try to fit the data to different mechanics models to understand what the properties of these cells are. And the one we're going to do is back here again. Oh, nope, dang it, went the wrong way. We're going to do the elastic solid model. So in this model, we assume the cells are linear, elastic, homogeneous, isotropic materials, which, as we have been talking about in this class, is totally not true, right? They are really not homogeneous and isotropic, especially if you look at the smooth muscle cells, right? Like the ones that are actually muscly are like all shaped this way with all these fibers in one direction. That's really anisotropic. The ones that are more spread out and fibroblastic are really inhomogeneous. They're like spread out. There's like parts with lots of actin, parts with not so much actin. But as a first approximation, we're going to make this approximation because it's easy and everybody does it. And if you're assuming, if you fit it to the data for small indentations, as a first approximation, most materials at very small indentations look elastic. And so it's not a bad approximation as long as you don't fit it to the whole curve. You're going to fit it just to the beginning part of the indentation. And so again, that's another point where you have a decision to make. How much of the data am I going to fit to this model to get a modulus? And you'll play with it and you'll see there's definitely, like, at some point it really will not fit the data at all. So you need to decide what part of the data I'm going to fit. If you want to get fancy, so those of you that have probably used MATLAB before, because it's hard to do in Excel, you can also fit to a little bit more complex but still pretty simple models. So these include viscoelastic models. So I have a cell, I know it's not elastic. Does anyone know by looking at the data how I know for sure it's not elastic? We talked about it. Like, what in that curve really makes it obvious it's not an elastic material? Yeah, the starting and ending point, right? You have hysteresis. Yeah, pushing in and coming back out. Don't go back and forth on top of the same thing. So that's due to viscous dissipation. The easiest way to model viscoelastic type properties if you think about elastic properties as being a spring, if I add a dash pot, it gives you loss. So that's all the mechanical people call it. As an electrical engineer, it's like a resistor and a capacitor. So these models, that's all they do. And so very simple one looks like this. You can get really fancy and add many dash pots. And basically all it does is it gives you a decay constant. So each of these dash pots has a time constant associated with it. And that will determine kind of the shape of that return, the viscoelastic return. Very important for these models, the one thing that you really need to know is how fast did I indent the data, right? Because I did it at 1 micron per second, so the response of these dash pots depends on how fast I indent. And in actuality, if I do the experiment and I indent the cells at different speeds, I will get different looking curves. If you want, you can get fancy and do something like that. I think that's kind of the background I wanted to do for the experiment that we're going to do for the class exercise. We're not doing the experiment. I give you the experimental data. Are there questions about it? Before we're in the room over there and everyone gets frazzled, does it kind of make sense? Are there questions about what the goals are for this afternoon? So we're going to take the data, download the data. You have two options at that point. You can either pull it up in Excel and just work in Excel. It's okay. You'll learn a lot. You'll be a little limited in the kinds of things you can do. If you're more comfortable with MATLAB, you can definitely load the data into MATLAB and play with it there. Fitting functions is much easier in MATLAB. So if you're using Excel, there are methods of having Excel fit data for you, but it doesn't work very well. So what I would recommend, because this is an exercise so you get some understanding of this kind of data, is to manually try to fit the data. So put this function into, you're going to say like a column that says force equals, and then distance from whatever the column of distances are. You have whatever your radius is, and then you have a cell that is going to be the modulus, and then you're going to manually change the modulus until the curve on the graph looks like it matches. As I said, there's a way to make it do fitting, and if you know how to do that, great. Every time I try to do it in Excel, it crashes. And then again, we're using this equation because we're using a spherical tip, not the cone. So step one, put the data in either MATLAB or Excel, convert the data from raw AFM data to a converted force distance curve, talk amongst yourselves and figure out where you're going to put the contact point. And then we're going to stop for a bit there and compare what everybody did. So I've done this exercise before, and every time I do it, everybody puts it in wildly different areas, and I will be honest, no one is really wrong. And that actually shows you kind of why you need to think about these things, especially when you're reading papers, because it's important to know. And then once we do that, then we're going to fit to these models and look at the data again. Make sense? Okay. I think that's good. So you can ask questions, or otherwise we'll go to lunch and come back to the room at 1:45. Says yes. Go. But I'll be here if you have questions and you were trying to ask. Yeah. If you have your own computer, that's okay too. Just, yeah. Did everyone get the data? The data for today. Did you get the data? Okay, good. Okay, well, during lunch we will email you. And then I will bring a USB key.
So let's take 2 articles. Maybe we have to get the data. And first I would like to say that I am not a nanomechanical person. In fact, I am neither a nano person nor a mechanical person. I am basically a biotechnologist, biochemist turned into biotechnologist. And my association with Dr. Delphin is not related to nanomechanics. Unfortunately, this turned into a nanomechanical courses because of her expertise. I associated with Dr. Delphin for a project on 3D printing using a low-cost printer. You know, all the 3D printers are very expensive, especially when you want to print a biological material. No, they cost more than crores. So her work, in fact, I have not emphasized that work. I mentioned it as device development for economically poor settings. That's the only term I used. But what is her work is mainly on making low-cost glucose strips. Very low-cost glucose strips, which will be very needed for both the developing countries and the underdeveloped countries. So it's a very interesting work. So those who have a time, and she has lot of video lectured publications. What is the journal called? Joe. Journal of Visual. Joe. It is called a Joe. Just don't brush it as Joe. You have lot of visual manuscripts, visual articles which get published in the Joe. So the work like making a very versatile modification in the printers, how to use the printers, everything is video session with the author explaining their modification and usage of such materials, etc. So you just look into the term called Joe. So we are also trying to mimic the same thing. In fact, one of my students, fintech student, he modified a low-cost Epsilon printer. It's a just 10,000 rupees printer where we can, a typical printer, you have to insert a material like a paper which will come out in the reverse direction. So, and you have to have a control of the printing through the interface computers. And if our objective is to print it, so my objective of doing the 3D printing is not a glucose oxidase printing. I work with neurodegenerative disorders, so we want to print a live neurons like an array and study the interaction of these neurons with various molecules. My objective is to study the interaction of these neurons with amyloid peptides. So we want to print a live neuron on the 3D printers and see whether it is, how long it can sustain its life, whether it's viable, etc., etc. So that is the objective. So we have made an attempt to work this and we got a very good initial results which has to be taken forward. In fact, we are trying to make an article to Joe only, and let me see whether it will work out or not. Okay, that is my association with Dr. Delphi. And interestingly, this Jan advertisement came and we want to bring her for interaction further towards 3D printing work or tissue engineering, because as you know there is an active group working in our department. Dr. Anantharamanan is doing a lot of work on tissue engineering. And Dr. Viveka in the nanomechanics, we want to utilize her expertise in further collaboration on all these research topics. So we want to have an opportunity to bring her here and Jan helped us in a way to bring her and we want to collaborate. We want to take over this collaboration to next level for applying the research projects, joint research projects, etc. And as I said, even outside participants, please utilize this opportunity. And one thing I like to thank Dr. Delphin is his promptness. Though he is so many miles away, even in Tanzania, he used to reply immediately to her. I phone in an immediate response. And I never expect such a prompt response from one person who have never seen her. I am seeing her only now, like just 3 days before or 4 days before. But without seeing the face, and you have to do so much for one unknown face, for that you should have a very broad mind. I have to really appreciate her and thank her for this. I don't know whether I get an opportunity to thank her separately or in a forum, but I take this opportunity to thank her. And from the day she landed till now, she never complained of anything because we complain a lot. About our environment, about our facilities, etc. And one word she always utter is great. And that is her greatness. So I think really take this opportunity to thank her. And my lecture is again as I said, don't ask me too many of technical questions. And that is first thing I want to say before I start the lecture because I am not a nanomechanics. But I want to utilize this opportunity to do something or utilize like you I am also learning. So how to use these mechanical parameters to study some of the aspects related to neurodegeneration and how to take forward this knowledge to the next research related to my area. She said your disease of interest. My disease of interest is always the liver disease because I am working with the liver disease for more than 15 years. And I want to do something for those patients whom we are associating with them for more than some 5-10 years and the way they suffer because there is no cure for this disease. As you know, for all the neurodegenerative disorders, there is no cure. So only way to help them is how to prevent them or diagnose them at the early stage. So our approaches are more towards this. Okay, so let me move on to my topic, cell mechanics. By now all this introduction, I don't think I need to say much about the cell and why the cell is a machine and how the cells can generate force, sustain the force and how these forces are very important for a physiological function of the cells and body and the tissues, etc. And as we know, the cells are very active material which respond to the external stimuli through mechanotransduction process. That mainly by arranging the cytoskeleton and reorganizing the cytoskeleton and post-generation. And if there is any abnormality in this process, for example, genetic mutation or any pathogen infection, they causes the change in this reorganization of the cellular materials, thereby causing a disease. So our objective is to look into how to quantify these cellular properties in normal physiological process, which you have studied for past 4 or 5 days, enormously various techniques used to quantify these cellular properties and how this process can be correlated with the abnormal physiological conditions like pathogenic conditions. And some of the very basic examples where the force is generated, sustained and detected, which is very important for everyday life, very important one is the respiration. So when you take a deep breath, you know how many cells and tissues are getting stretched out. And that is a very important to pump your air to from the lungs to entire body. Similarly, stretch outs. Why you have to stretch out? Increase the blood circulation. So vasculoelasticity of the blood vessels is another good example of the forces which are very, very essential for us to sustain the basic life. Similarly, you do have lot of examples like skin, which provide a mechanical barrier and also for mainly to application of external stretch. Thereby, we all know how it will be a barrier for entry of pathogen or other toxic molecules, etc. Another very good example is a skeleton. As you know, it is a structural support to sustain the force of gravity. These are a very basic example. We all know that the mechanical properties of the cells and tissues and organs are very, very essential for a normal physiological function. Okay. So which are all well worked out for the last 3 days. We have been hearing the same thing. Cell is a machine. Cell generate mechanical forces and these forces are very essential. Can I have the next slide? And again, basic mechanical properties, when you talk about the mechanical properties, again, the major mechanical properties which we have to study or quantify in order to characterize the cellular mechanics are the stress, shear, the two important parameters. As you know, it's a very basic elementary projection of what is stress and what is strain, etc. So you people are much more expert than me. I do not study the engineering concept. But you know, stress is force by area and strain is deformation by length And all these parameters, mainly stress and strain, cell undergoes stress and strain with the application of mainly during the tension, compression and shear process. And one of the important parameters which we always use to quantify the stress and strain related to a solid is a Young's modulus, which is a constant and which is a very basic parameter to define the or to scaling the stress and strain in the solid condition. And regarding the liquid, it's very complex. You have additional parameters like viscosity, elasticity. And most of the materials are neither solid nor the liquid. It's called a viscoelastic. So you take up elastic modulus, another parameter coming into picture. So all these parameters are very basic parameters which we have to quantify through various techniques. And the slide is the bottom line. The stress and strain, generally when you talk about cells, they are very viscoelastic. So the stress and strain are generally it is not, sometimes it is linear. When you have a very minimum strain, the shear force is going to be linear. Whereas when you keep on increasing the strain, there is a non-linear behavior of the cells because cells are not going to be never going to work in a either in a solid state or in a liquid state. Is called viscoelastic state. So cells just behave in a non-linear form when you apply a stress. Its shear forces are non-linear. Can I have the next slide? And this slide again, I think it is been projected n number of times in this forum. Why these slides are important? Because again, as you said, when you want to quantify these mechanical properties of the cells, there are the choice of the tools which you select or the techniques which you select are depend upon the three important parameters. One is called a length scale, another one is called a time scale, and the third one which I am going to project is elastomodulus scale. So like in the length scale, we know what is the material you want to characterize. You want to work with the nanomaterials or micromaterials or the materials which are of larger like tissues or organs. So depending upon the characteristic of the material or the length scale of the material, you have to select a suitable technique. So obviously the entire focus of us will be on nano scales. But initially when the biomechanics starts, most of the earlier studies, 1980s, 90s studies are mainly focusing on the biomechanics of the organs and tissues, where how the bone can sustain the weight, similarly how the muscle can, what extent the muscle can tolerate the force, etc., which is generally being studied at a larger length scale. But with the more advancement in the techniques like what you are talking about, all this AFM with the indentation and all the other techniques which we've been covered for almost 3 days will help us to move from the organ and tissues which are larger dimension to the micro and the nano dimension, and now we are so very good even to study the single cellular mechanics. We can even study the mechanics of the single cell. Single molecular mechanics has been elaborately been dealt already. So it is an advancement of the techniques which helped us move from macro scale to nano scale and single molecular scales. So we have to really thankful for those technical advancements so that we can able to study what is going on in the single cells, whether under normal physiological condition and also in the pathological condition. How these parameters can change in the pathological condition. Okay, similarly, time scale. Again, we have to measure the various cellular activities as mentioned in the slide, nanoseconds to days and hours. Days and hours we can study very easily, right? Anything which happens, for example, cell division. We are studying the cell division and mitosis for more than 100 years. But we are able to study the protein dynamics and other thing only now. We can't even see a protein except for crystallography which has been developed from almost 70-80 years. But you can even see a single protein molecule and how it moves, how it dynamically interacts with other ligand molecule, etc. like what she has delivered in the morning lecture. So such things are possible which are occurring in a nanosecond scale only with the advancement of these techniques. So we have to, like rightly like Delphin said, we have to select a suitable techniques depending upon what is the material you have in your hand and what is the process you want to study. So that is where the choice of material and the choice of techniques are very, very important. Though everything is available, it's not possible for us to use everything. Sometimes nothing is available. That doesn't mean that we can use, like let's say you can use an optical microscope from the start, but you have to move on to high resolution spectroscopy techniques and the AFM, etc. if you want to look into the nano levels. So the choice of these materials and choice of the process which you want to study is very, very, very important for you to select a suitable technique. And another important parameter is elastic modulus. From the morning she was talking about the elastic modulus characters of the cells. How to quantify them, for example, it may be from kilopascal to GPa. And the process may be, you may want to study a single cell or it may be a very complex tissues like bone, etc. So again, the choice of material and choice of the properties of the material is another important parameter which you have to take into consideration if you want to select a suitable technique to study the cellular properties. So I just want to recall saying that we have learned everything, and we have, when you want to apply this thing for a research or for any other analysis, we have to take all these things into consideration before you plan our research activities for a particular objective. What are the, and this slide is again going to overlap. So the techniques which you select are huge. There are huge different techniques are available for us to select, like optical traces. Have we completed optical traces? Because I was not there for that lecture. But anyway, you must know when to want to. For example, I put one question. I want to study the compressive properties of the cells. I want to study how much the cells can undergo the compression during the external force application. What is the best technique you can select? Again, I say cellular mechanics. What could be the choice of your technique? So that means we are not analyzing, right? We are just learning the technique. For example, I want to study the stretchability of the myosin. What is the technique which I want to take how much muscle myosin is stretching during a particular exercise or particular process? What is the technique which we are supposed to use? AFM is the correct technique? It's a reverse. When I want to see the compressibility, obviously it's AFM and AFM with intention. When I want to study the stretchability, optical pieces. So we have to analyze what is the physical parameters or mechanical parameters we want to study, choice of material. Again, what is the dimension of the material which you are talking is also very important. So please recall. So this is again a recalling session. So he is going to talk of fraction force microscopy sometime tomorrow. Yes, it's tomorrow's session. So there are other better techniques are also available. Please listen carefully and see how we can apply this technique suitably. That's very important. And the next session. Okay, so with all these basics, again, I'm not going to go much into all these derivations. We have seen a number of derivations, very complicated derivations of it. So with the very basic recalling of what is cellular mechanics and what are the mechanical properties we can measure, I want to take two examples, classical examples, where there is a change in these mechanical properties of the cells which are responsible for pathology. So two important cases, one is on cancer, another one is because he is again an expertise in studying the cancer mechanics, and I want to explore what could be the possibility of studying these things in a neurodegenerative disorder. So I have taken two classical case studies of concepts, one on mechanics, change in cellular mechanics in cancer, and why we have to study it. Some question on why I have to study all this complicated complex process. At the end, where do we use this knowledge? Unless it is applicable to some drug development, diagnosis, or treatment, why I have to study all these things? Science is interesting to study, but ultimately being an engineer, you want to use it something useful. So The next two concepts I want to emphasize will be how the cellular property changes during the tumor development. Again, I am not going to specific tumor. There are a lot of literature available, as I said, in the literature, mainly on prostate cancer, localized cancer like the breast cancer and the prostate cancers, because they are entirely localized. So they are, we are going to talk of much of the properties related to cancer properties, mainly on the localized cancer, whereas lymphoma and other things are highly different because they are in a fluid phase. So the cellular property of these fluid materials are entirely different for a lymphoma and other related cases. So we are going to talk about some of the mechanical properties noted during the tumor development and how these can be studied using various techniques and what is the application of such knowledge. Okay, so we all know cancer is due to abnormal growth of the cell, which can arise due to dysregulation of signaling pathway. Because those who have studied the cell biology, you know, the cell has to maintain its three-dimensional structure, contact inhibition. If there is a loss of contact inhibition, how it leads to differentiation of the cell uncontrollably, and how these modified cells can be regulated by apoptosis, and if there is a mutation in this apoptosis, how it can cause the cancer. So all those basic things we are all studying. And the major cause for most of these cancers are like mutation in the genes, which are expressing the protein which are involved either in cell proliferation or in apoptosis. And the mechanical properties of these cells and their surrounding environment, mainly extracellular matrix, changes very huge during the tumor development. Can I have the next thing? And the most important problem with any tumor is metastasis. The cellular properties are a very important parameters which governs whether the cell, whether the tumor has to be, whether the tumor cell have a tendency to be in a localized environment or they want to move from the one environment to another through the circulatory system or lymphatic system. We call it as metastasis. So this slide is very complex, but as you know, the first part, when I say one, initial stage, the cancer cells recruit the stromal cells, which produce a lot of growth factors, adhesion factors, etc., which will help to remodeling the extracellular environment. When I say CAF, is a cancer-associated fibroblasts, which mainly produce a lot of adhesion molecules, integrin molecules, etc., which will help for the cancer cells to adhere on the surface and move through viscoelastic properties. Okay, and another important concept will be angiogenesis. As you know, the development of new blood vessels and degradation of extracellular matrix, which are the ones which are associated with the tumor progression and tumor metastasis. Because once the cells started growing in a very closed environment, because of the compressibility, because now that's where the major cellular properties are this. Because of the growth of the cells, you have a compressive growth. Compression is going to occur. And because of the compression, inflammatory process will occur. And because of that, there is a fluid accumulation. So it will alter the shear force of the cells. Because of all this, the extracellular matrix of the tumor are cells which degrade. Because of that, the cells try to move away from the localized environment through the circulatory system. Thereby, it has a tendency to develop it as a secondary cancer through metastasis process. So the most of the cellular properties which are generally been modified in the tumor environment is mainly the major type of stress the cells can enter, especially tumor cells can encounter in a tumor environment is tensile stress, which are mainly caused by actinomyosin contraction, which are mainly responsible for extracellular matrix stiffness. Okay, and compressive, as I said, tumor start growing, tumor expansion, which results in the due to the uncontrolled proliferation, they have a tendency to move away from the particular space because of the compressive stress. So these are the major stress the tumor cell environment has. And shear stress is, as I said, because of the vascularization, angiogenesis, etc., or fluid accumulation in the cells. Because as I said, when I say stromal cells, obviously inflammatory cells comes into picture. Inflammation also occurs in the tumor environment, which leads to generation of lot of cytokines like tumor necrosis factors, tissue necrosis factors, which are all contributing for the interstitial fluid flow in the tumor environment. So the major stress the cells encounter during the tumor development is tensile, compressive, and shear stress, which are the major factors which decide whether the cell has to be in has a tendency to be in a localized environment or it wants to move away from the environment, leading to metastasis. Can I have the next slide? Okay, some of the change in cellular properties which has been reported through extensive review and extensive research are decrease in cell stiffness. As I said, when the cell want to move away, it can't be rigid. So only only when it is very flexible, it can move through the extracellular space and then come out and then they spread through the other cells or other tissues through circulatory system or lymphatic system. Decrease in actomyosin contractibility, again, because they are going to be, if the actomyosin is there, they can contract and relax, but they cannot reduce the size. So they want to move away easily, so the decrease in actomyosin contractibility and change in the in extracellular environment and stiff extracellular matrix, and these are the major mechanical properties which are usually altered in the tumor environment, and people are trying to study the change in these cellular properties as a cue for whether that particular cancer has a tendency for metastasis or not. So you just take the cells through biopsy from these cancer patients and study the cellular properties, like what we are doing in the in vitro study. And based on these shear and how they respond to these tensile shear or contraction shear or other shear forces, people are trying to diagnose whether the particular tumor has a tendency to metastasize or not. So this is now being used as a diagnostic tool, and usually many of the cancers are generally diagnosed as a secondary cancers. You don't even know where is the source of the primary cancer. Okay, so again people are trying to see whether what could be the origin of these cells and whether they are metastasized from the bone or from the other tissues, etc. So they are helped to diagnose or metastatic behavior of the particular cancer cells can be looked into by studying these cellular properties. Okay, so the major forces, as I say, tensile, compressive and shear forces as represented in the here. Generally, both the compressive and the shear forces are generally parallel to the cell, whereas tensile and shear forces are parallel as shown in the thing, whereas shear forces are generally perpendicular. They apply generally in a perpendicular. So people are trying to study all the shear forces as a cue for metastatic behavior of the cells, and that there are a lot of AFM and other, as I said, whether you want to study the compressive behavior of the cells, tensile tolerability of the cell, or shear force of the particular cell. So depending upon what is your objective, use a suitable technique, study this, compare it with the normal cells, and that's what you are trying to do in your lab, right? You are trying to study the cell behavior in two different conditions. Same thing here, you try to take a cancer cell and compare these forces with the normal cell and see whether they deviate or there is a change and whether it can contribute for the metastasis. Okay. So when the cells are in a low mass, you know, the extracellular matrix has a low tumor stiffness, but due to the molecular Dr. Viveka mentioned about the mechanotransduction pathways. Because of the external stimuli, lot of mechanotransduction pathways getting activated, leading to the expression of lot of proteins like adenosine, cancer enhancing protein, etc. So because of that, the cell have a high tumor stiffness and leading to the tumor metastasis. So all these behavioral changes, cellular behavioral changes are one people are trying to look into and study and say whether we can predict whether this particular person have a tendency. Because again, not all the patients with the breast cancer or a prostate cancer will have a secondary cancers. So again, this is, though we call it as very, very complex process, again, it varies depending upon the individual person's response to particular stimuli. Not universal, right? Each cells are different. Though we call it universal, cell properties are universal. The behavior of the cells to the external stimuli is highly a variable parameter for depending upon the environment and the extent of stimuli you get, etc. etc. So try to quantify them from a particular individual, and you can say whether they have a tendency to metastasize or can. And again, the change in the microenvironment between the normal tissue and the cancerous tissue. Mainly you look into solid stress, shear stress and interstitial fluid accumulation causing the shear stress, etc. So all has to be studied. It's an representation. So this slide explains the interrelationship between the various stress and the tissue response during the tumor suppression. For example, when there is an intracellular tension occurs because of the active myosin contractibility, this leads to ECM stiffness. When there is a ECM strictness, it ultimately leads to solid stress because of the compressibility of the tissues, which in turn further enhance the intracellular tension. So there is a cause and consequence of all this interrelationship stress is very important to look into, and it's not a one way. In some direction it's a two-way, in some direction it's a one-way. So quantifying all this are the cellular properties or cellular mechanical properties are the one scientists are trying to do and compare it to the normal cells and see what could be the variation and how this variation could be correlated with the normal cells or metastatic behavior of the cells. Okay. And why do you want to study this? As I said, you have now what I want to say will be, as you know, there will be a change in the cellular mechanical property during the tumor development and progression and metastasis. And once you want to study, once you have studied this, how to apply this knowledge for developing the drugs. For example, a lot of potential therapeutic approaches have been initiated by scientists targeting this change in cellular behavior. For example, inhibition of cell contractibility. I said cell stiffness is the one which leads to metastasis. So people are trying to minimize the active myosin contractibility in the tumor cells. So the drugs which are targeting the inhibitors of JAK kinase, STAT kinase, as you know, these are all the molecules which are involved in the signaling, mechanotransduction signaling pathway. So people are trying to develop the drugs, and one such drug which is in the evaluation phase, clinical evaluation phase, is ruxolitinib, which is which is an inhibitor of JAK and STAT kinase. Thereby, it helps in the reduction of cellular contractibility. Okay, and the second one is the drugs which are targeting the solid stress and interstitial fluid pressure. For example, hyaluronidase is an enzyme which will degrade the extracellular protein, mainly hyaluron, to release the fluid which are accumulating. So when the fluid accumulates, as I said, it increases the interstitial fluid pressure and then also the compressibility of the cells. So if you want to release this, another way this drug helps is it also weakens the extracellular matrix and helps the drugs to get entered into the tumor so that the tumor responds to the particular drug more effectively. Similarly, you have angiotensin inhibitors which are mainly targeting the vascular system of the mainly tumor, thereby decreasing the interstitial fluid. As you know, it is a vasodilator, so it will dilate the blood vessels, thereby reduce the interstitial fluid pressure and make the cells to perfuse easily so that the drug and other molecule which you want to deliver to the tumor will be delivered more effectively. Similarly, you do have the approaches to modulate the ECM stiffness like inhibitor of TGF-beta, HCOP signaling pathway. These are all the ones which are associated. I am not going into the elaborately, but how these approaches are helpful for the scientists to target the different phase of the cancer so that it could be effectively being targeted for the drug delivery. So, lot of such approaches. I just mentioned only 3 because again it's a very vast area. So, the main concept behind this slides are the change in the cellular properties during the cancer are the very good target for not only diagnosis of metastatic behavior, drug development and drug delivery. We already said how this more effective drug delivery can be approached by altering the cellular properties. So all the 3 phases of the cancers are now focusing on studying the cellular properties of the cancers in a pathological sense. Okay, so this is just an outline. As I said, I am not an expert. I just want to say how the Viveka was bringing about the GI system, how it can be studied. Here it is a cellular system, like how the cancer cells can be studied and cellular properties can be modeled during the process, how it is modulated and how it is being targeted for the drug design, development, drug design, delivery and diagnosis. So it's not optional where just take any review, you will get this information. I'm just bringing it in a short notice for your that's it. So, but Alzheimer's disease is, let me say it is my favorite disease. Not because I want to get it. Nobody wants to, because I pray for everybody, no one should get this disease. But I have seen the more than 50-60 patients for past 10 years, how they suffer, and many of them lost their life by now. And it's tragic. Because you should know who you are. Once you start forgetting your name and you depend upon your caretaker for everything, like this happens. By now itself, you know you can't depend on anybody, even your own son or a own daughter when you are in old age. You have to be independent, and I want to pray God for everyone that when we are good and okay itself, we should go. We should not depend on anybody. But the life for Alzheimer's patients are really hectic. They can't even, as you know, it's a memory loss disorders. They can't even recognize their name. They can't even recognize whether, they can't even remember whether, once they go away, the major problem with the Alzheimer's disease patient, once they go away, they can't get back to their house, say, once they lost, they are lost. So in fact, being an engineering institute, we are also developed a tracker and a communicative device. Just start with them, it automatically sends a signal where they are to the caregivers. So we have made a lot of initiative, and in fact, that project has been selected by MHRD, and it's not MHRD, it's called Ministry of
MEIT.
Ministry of Health for Disabled Persons. So this project has been selected as one of the best projects where we made a prototype, and they want to take this prototype to the business model. So that automatically it sends a message. It again achieves your mobile-based technology. But now, if you want to, because where you are, if somebody wants to find out, they have to approach some higher authorities where they won't tell where the SIM is. But we developed the technology where it automatically sends the SMS to the caretaker for every 5 minutes. We can modulate the time. And we do have an SOS button in the device. Just by click of button, you can the person can communicate, but they have to click a button. But even if they forget to click a button, you have an SMS messages to tell the caretakers where they are. So we are trying to do some device development in this contest, which there are a lot of devices available in US. We are trying to make a low-cost device. Again, as you know, when we import something, it's going to be expensive. We go being India now trying to concentrate on Make in India. We want to do some products for ourselves. So this project being funded by DST, and we have submitted a prototype which has taken for an next-level business model. Okay, so that is Alzheimer's disease and the thing. So how the nanomechanics is applicable for the disease? That is, I'm just away from my topic. But anyway, because we should all know, because you might be having elderly parents or elderly grandparents who have a memory loss, etc. So please help them. That's the first request I have. being young ones, you won't understand the difficulties in life. But there are a lot of difficulties the elderly person faces in life. One main problem is your memory loss. That too, when I say Alzheimer's disease, total memory loss. That's the worst part. So before I go into Alzheimer's disease, I have a small video. There are two pathological factors which have been well established for a cause of Alzheimer's disease. One is called an amyloid protein. Another one is called a microtubule associated protein called a tau. So how this protein
Over a century ago, German doctor Alois Alzheimer spotted anomalies in brain sections from a patient with dementia. Over a century ago, a German doctor called Alois Alzheimer spotted anomalies in brain sections from a patient with dementia. Ever since, people have been studying the strange plaques and tangles that he saw, in the hope that we could one day understand and cure what is now known as Alzheimer's disease. Plaques are insoluble deposits of a peptide called amyloid beta, A-beta. They're formed when a protein called amyloid precursor protein is sequentially cleaved by two enzymes, beta and gamma secretase. Other molecules are generated by this cleavage and may play a role in the disease, but A-beta is the main culprit. A-beta tends to misfold and become sticky, eventually clumping together to form soluble oligomers. Some of these aggregate into large insoluble fibrils that deposit in the brain as plaques. The oligomers come in several forms or species. We don't know exactly which species are toxic, but research shows that they weaken communication and plasticity at synapses. This could be what stops the brain from forming or retrieving memories. Neurons aren't the only cells affected in Alzheimer's disease. Astrocytes and microglia also play a role. Microglia are immune cells that clear out waste and prune synapses during development. Microglia take up A-beta, but they also get activated by it, triggering the release of inflammatory cytokines that can damage neurons. The microglia also start to remove synapses by phagocytosis. As synapses start to malfunction and neurons die, abnormal patterns of activity emerge, and eventually the brain can't process and store information properly. Another key feature of Alzheimer's disease is neurodegeneration. Neuronal death and damage is triggered by A-beta, but some of A-beta's effects seem to be mediated by another protein seen in the brains of patients, tau, a component of tangles. In a healthy neuron, molecules are carried along the axon on a series of tracks, made of microtubules and stabilized by tau. But in Alzheimer's disease, tau is modified, causing it to dissociate from the microtubules, adopt an abnormal shape, and move from the axon to the cell body. Like A-beta, tau comes in a variety of forms, and we don't know which ones contribute to the disease. And like A-beta, these forms either remain soluble or stick together and deposit as the tangles that Dr. Alzheimer saw. Eventually, these processes kill the neuron. Another problem, seen in animal models, is that misfolded tau proteins can spread across synapses into healthy neurons. There, they make healthy tau proteins start to misfold as well, spreading pathology across the brain. The pattern of spreading through the different brain regions matches the changing symptoms from early to late stages of Alzheimer's disease. This pattern also reflects how certain neurons are more vulnerable than others to dying. Despite these advances in our understanding of Alzheimer's disease, no cure exists. While drugs are being developed to target amyloid beta or tau, it's unclear whether they will eventually be successful in treating the disease. There's only one certainty. Continued support for basic and clinical research will enable us one day to to diagnose and treat this devastating condition.
As represented in the video, amyloid and tau are two pathophysiological markers which are responsible for development of neurodegeneration, being in the cortex region of the brain, which are responsible for the memory function. So again, we are also doing some work in this line, wherein some of these markers which are developing in the brain can cross the blood-brain barrier and come into the plasma. Because there, as you know, you have a blood-brain barrier which is a tight junction which generally makes the brain separated from the rest of the system. But during this disease courses, lot of inflammatory process and other related process, the tight junction loses. So some of these markers like amyloid and tau, they move from cerebrospinal fluid and into the blood. So we are trying to look into whether the plasma markers could be utilized to diagnose this disease at the earlier. Because as I said, there is no cure. Once neuron, because I used to mention the same concept to the students. Neurons are very unique. Why? Which factor? They cannot divide. So once lost, it is lost. So new neuron has to come, because as you grow older, your stem cells also will be lost and there is no new cells, new neurons can develop. So once you lost the neuron which are responsible for a particular function is also lost. So the best way to solve this problem is try to prevent the neurodegeneration. So and some of these markers try to appear in the CSF and in the blood 5 to 10 years ahead before the symptoms comes. When I say diagnostic marker, you have to diagnose at the early, not after developing a disease. So once they say that they lost the memory and you know it's Alzheimer's, what's the point in diagnosing? No need for any marker, right? When they have a memory loss, then you can say they are Alzheimer's. There are other type of dementia I don't want to go into. So we are trying to look into some of the markers which can be predicting the possibility of getting a disease at an early stage, some 5 to 10 years ahead. So that is another area of research we are working on. Okay, so like regarding cell mechanics, this particular paper which I published in the Journal of Biomechanics, I have done the same groundwork of what you are doing. I was trying to look into how the cellular mechanics are altering in the brain or in the neurons during the neurodegeneration. So I got into this paper, Journal of Biomechanics, 2019 published paper, and they have done a very small work wherein they have seen the cellular mechanical property, how it is changes when the neurons are integrated with the amyloid peptide, and in the video is that different species of amyloid peptides are produced, and it's not sure which one is more pathogenic, but with a lot of studies it's proved that amyloid A beta 42 is more pathogenic than other forms of amyloid. So similarly in this particular study, they take a neuroblastoma cells, incubate with amyloid peptides at a different concentration, at a different time period, and study the cellular properties, mainly in the form of Young's modulus, and see how this Young's modulus changes, and what are the cellular properties changes, and how this can contribute to the progression of the disease. So the objective of the paper is this one, wherein you can see in the top, A beta, when it is in the monomer, generally it is easily being taken up by the neurons, by endosomes, in the neuron by endosomes, and it gets degraded in the liposomes. So it is not a problem. A beta clearance is very normal. A beta is produced in everybody. The amount of production and clearance is the one which are getting altered during the disease. We all produce A beta but at a very low quantity. So when they are in a low concentration, they get cleared from the system, no problem. But when they develop when the concentration become more, as shown in the video, they get oligomerized, and the oligomerized A beta enter into they make a pore in the neurons. They get, because of the pore, the calcium influx occurs. Because of the calcium influx, there is an increased osmotic pressure, which is again has to be measured as I already said, interstitial fluid changes the pores in the cell. So that also has to be measured, and because of the active polymerization, it enhances the stiffness of the neurons. So again they want to see, this is hypothesis they made, these are mechanisms which we don't know, whether these mechanisms can contribute to the alteration in the cellular property. So they want to measure all four properties, mainly increased osmotic pressure, enhanced stiffness and reduced stiffness when the concentration of the A beta become more. So they want to make this hypothesis tested in the cells. So they taken neuroblastoma cells, incubated with A beta at a different concentration at a different time period, and studied this cellular properties using what would have the technique they would have used? AFM with intention, because you want to study how much is a compression, relaxation, etc. So the one technique they were selected to quantify these forces are AFM with molecular intention, and they studied the Young's modulus of the cell. For example, in the first slide you can see the one which is given in the blue is the cancerous cells, neuroblastoma cells treated with a beta peptide, whereas the other one is a normal cells. Always you have to have a control, remember. So you should have a neuroblastoma cells and you should have a neuroblastoma cells treated with A beta. These two are the controls. One which is just a cell, another one is cell with the A beta peptide. They study the post Young modulus as a function of intention length. That just now she projected a big formula, the same formula is there, you can see. And as you see, E is a Young's modulus.
Up there. Why is it not exactly the same? It's not exactly the same as the one you did in the lab. Why?
The formula you can see, it's exactly not the formula.
It's a little different. Why is it different?
Because that is between force and distance. Between force and
Right. So you also had force and inundation, but their model is two.
Yeah, speed and model.
The what? The tip, right. So this one they use the pointy tip. So that's the formula for the pointy tip as opposed to a sphere. That's otherwise it's almost exactly what you did in lab.
And you see Young's modulus, and what you observe is as the concentration of A beta increases, as you see in the next slide, the Young's modulus increases, but beyond certain concentration the Young's modulus decreases, as you see. So what they are trying to project out of this study is, can I have the next slide? When there is a very low concentration of amyloid, for example 250 nanometer of amyloid concentration, which is generally a normal concentration, there is not much of change in the Young's modulus. As you see, control and experimental group always remain same. So what they so there is no osmotic pressure buildup or stiffness changes, etc. So the process could be the amyloid get cleared through the clearance system. So there is no change in the cellular properties. Do you agree? But when they increase the concentration, can happen thing. As you see, lower concentration to moderate and a higher concentration. So when I say moderate, it's around 750 nanometer of A beta peptide concentration. There is an increase in Young's modulus. But when again you increase it to a very higher concentration, the Young's modulus decreases. That is, at a lower very low concentration, there is no change in cellular property. Higher moderate concentration increase in the cell stiffness and other parameters, but further increase there is a decrease in the Young's modulus. How to explain this process? This is a result. How to interpret this result with the physiological or pathological process associated with the AD. Can I have the next slide? And this is where they are trying to modify, as you say, when there is a beta treatment, A beta get inserted, and because of that you have a tension stress to be accounted as a part of Young's modulus. But similarly, when there is a fluid flow, I say there is a pore, calcium enter, because of that interstitial fluid accumulate. So you have an osmotic force which has to be accounted in your cellular shear force. Similarly, when there is an active polymerization, you have another shear force. All these are the ones which are contributing to increase in the cellular stress or the force in the neuron during a A beta incubation. Okay, another next. Okay. Okay, so they want to analyze why there is a decrease in Young's modulus beyond certain concentration of A beta. And the hypothesis or the justification they are trying to do is when there is a very high A beta concentration, the A beta activates another signaling pathway called an ASK3 beta, which is an activator of the phosphorylation of the microtubule protein called as tau protein. Because as I said, A beta accumulation is the first stage, tau disintegration or microtubule disintegration is the second stage. So as the GSK3 beta, which is another signaling pathway which are being targeted for a drug delivery, again we worked on that also with the pharmacy college, that's another story. But when there is a signaling pathway of GSK3 beta get activation, it is a kinase. It is a kinase which phosphorylates the tau. So phosphorylated tau with the mini negatives are when they focus on one place, they have a reversible dose, like what we said. So they try to disintegrate from the microtubule, that's what you see in the video. Once they disintegrate, microtubule lose their structure. So when there is a very high concentration, another molecular pathway gets activated is a tau phosphorylation, which will lead to your disassembly of the microtubule, which is responsible for decrease in the stiffness of the neuron. That's the reason that low concentration, no problem, moderate concentration, stiffness increases, at a very high concentration, stiffness decreases because of the microtubule disassembly. So they can able to explain the process of pathogenesis very effectively with this cellular change in the cellular properties. This is just a very small study just to say how the pathological process can be studied by looking into cellular properties. Do you agree or not? And how this could be used for a drug development, etc. is an expert. For example, both are pathological markers. Which one to target effectively if you want to make a cure? Again, no permanent cure, at least to delay the neurodegeneration. So by this process, you must know amyloid clearance is better than tau because this is the one which mediates that process. So if you have an approach to prevent the amyloid polymerization or oligomerization, or if you enhance the clearance mechanism, then that would be a better approach than trying to eliminate the hospitals. Okay, so these are the very simple studies people can do to understand the pathophysiological mechanism. So I just borrowed this information from the particular journal. So maybe you are also going to do the same exercise tomorrow or day after tomorrow when you want to present. So what we have to understand why, and that's why I say first you should know what is the objective of your study. Then you should have a background information how these properties are generally altered or not. Then you design an experiment study and then interpret and then. So this is a very small exercise which we have done to justify my topic. And but I want to do something on this line on course. Because as I said, my objective here is to make a because with one of my research scholars around, we work with another protein called a RAGE. It's a receptor for advanced glycation in product, which generally now been recognized one of the receptors which are used for the which is also uses A beta as a ligand. It's a multi-ligand family receptor. So now recently they have shown that amyloid beta peptides are also here. One which binds, and this protein exists in a multiple forms. If the protein is in a soluble form, it tries to clear the amyloid peptides, but when the protein is in a membrane-bound form, it increases the inflammation, leading to both pathogenic conditions. So we are trying to see whether this whether the amyloids have a better affinity for a membrane-bound form or a soluble form. And there is one study which has been shown very recently that if there is a mutation called a G82S, if single mutation makes these people more susceptible for AD. If the people with the RAGE mutation at the 82 position, if they changes the normal glycine to serine, their possibility of getting the disease is 40% higher. So we want to see why this mutation causes a different binding affinity of these receptor for the peptide. So if you want to study these binding affinities, you want to use this study. thermal calorimetry study, where we will measure the forces between the interaction. But another way I could study was whether we can, because that's where we already started we have clones that we made a side-directed glucogenesis, and we have a two neuronal cell lines which are expressing these proteins differently. If we want to make such arrays or in the soluble case, if we want to study such interactions, it will help us to at least know why is a single mutation increase that is very high. And how to solve this problem. People with this mutation, definitely they are going to get a disease. Sure. If I can able to find out the mutation in a particular family, then they can look for some of the therapeutic approach or minimize the possibility of getting these diseases. So we are trying to work on this line. That's what I said. I want to make an array study the ligand interaction for two different proteins with the amyloid. If it works out, then it will be through your expectation and mechanics I want to study. That is another thing. So with this small outline of the work which are done by some people, I would like to say we have to learn something new every day. Otherwise your brain will die. Neuron. Right? I tell you, one of the way to activate your neuron is give work. That's where all your Sudoku or other things are helping, because you have to keep activating your brain. That is the only way to make your brain to sustain and work. Otherwise it will die. Okay. Thank you very much for this. Yeah, people for now, because remember it is it's also there is a hereditary background for this disease. There are two genes which are involved in the hereditary familial form of the Alzheimer's disease. When I say familial, they get it. The entire family members get it. There are two genes. One is called pre-senilin gene. If there is a mutation in the pre-senilin gene, people with this mutation in this gene, the family used to get the disease at the age of 35 to 40, not 70. Others is after 70. Other non-familial Alzheimer's disease, multiple causes, stress, major causes, inflammation, lot other causes, right? So for those people above 70, we will show that above 70. So all our patients are 70 to 80. So you know how much they are, how fragile they are, how difficult to manage them. But familial diseases are not prominent in an Indian population or in an American population. Yeah, there are grades because we quantify the dementia in these patients as mild, moderate, and extensive. We have a questionnaire-based method, which just answers memory-based questions, language-based questions, etc., and we grade them. But again, people with a mild will turn into moderate dementia patient maybe after 5 years. They are not going to remain as mild because neurodegeneration, once it started occurring, it is a continuous process. So even the amyloid which enter into the another neuron, deposit in another neuron, the next neuron dies. That's why it was neurodegenerative. It's a continuous process. Once it started occur, it's going to occur very fast. So best way to prevent will be try to minimize the course of symptoms. Then we do have a mice model where I said pre-senilin mutation. They just induced a mutation in this mice. It's called AD mice. But the AD mice are available. In that context, I am happy to say there is a National Brain Research Center in IISc Bangalore. Dr. Vijay Lakshmi Ravindran group. They got a big project from DST where they are the national resource for us to deliver AD mice. They have a breeder mice where if you want to work on AD mice, because each mice costs me 1 lakh. One mice 1 lakh. But that is not a normal mice, it's called an AD mice where they have a mutation in the pre-senilin gene, which generally gives a symptom very similar to human AD. So there are models available, and there are cell line models are available. This is a cell line model, and we also work using this cell line model for the studies because of AD mice being expensive.
about the cell line for the AD?
Yeah, this is available national cell line Pune.
AD cell line, we tried.
AD cell line is not specifically, it's a neuroblastoma cell line. You differentiate, and this is a cell line that has a tendency to accumulate A beta. Because of that, it's called an AD cell line. It's not exactly AD cell line. You have to differentiate this cell line in the presence of retinoic acid, so they differentiate into, because as I said, neuronal cells cannot be retained as neuronal for longer time. So neuroblastoma cell line, they receive it, they treat it with retinoic acid, convert it to the active neuron, then add A beta and other things. And it has a tendency to accumulate A beta. So because of that, we call it as AD cell line.
When the Young's model reading came down, how do you know it was microtubule disassembly?
Yeah, because there was one slide with the screen which, sorry. It's a good question. I forgot to mention this. This is a study, the same study, where they are seeing the microtubule assembly through the fluorescent tags. I should have confirmed this. Thanks for being a scientist. So the hypothesis has to be tested through the validation. So they have made a microtubule assembly study using labeled tags, and you can see that in the normal cells, you have a well-organized microtubules, but when the concentration or a time period increases, you can see there is a microtubule disassembly, very serious disassembly when it is a larger time. So they correlate these properties with the microtubule disassembly to conclude this. Thank you. It's a good question, and I should have justified this.
Madam, when you convert the neuroblastoma cell to AD by...
I won't say AD. It is a AD model because it has a tendency to accumulate amyloid and give various pathological features, mainly the neuroinflammatory pathways and other things getting activated.
That's what that model actually, people usually say that even in a mice model is not coming same.
Yeah, any model is not an exact model. But I can't work with AD patient. I cannot try all the things with the AD patient because already they are very old, they are suffering, and nobody will allow me also, ethics. So any trial I cannot do with the AD patients. It has to be tried at a cell line, in vitro cell line model, then with the in vivo mouse model, then only it can be taken into the clinicals. So we do have ethics. We cannot work everything with the patients, be it a cancer or any other disease. So we have to look for a closest working model. Okay, so if there is no more questions, thank for your patient listening, and we have a very interesting session to go. I want to say that Dr. Delphine is a very good ballet dancer. You must have realized during her presentation itself that her walk and talk itself is like a dance. You all agree? So I just requested her to make a small, it's a very video. Let us enjoy the you know what is this?
Dr. Indian is very good.
Yes, he also mentioned it in her lecture. So let us witness our dance. Enjoy the dance.
Just a quick thing, it's rehearsal footage and it's not my favorite ballet, just what I happen to have on my laptop. But I will say, I get asked about it a lot, and I think it's important. We're all scientists and engineers, and we work a lot in the lab. It's important to have something outside of the lab to like with your brain, right? We exercise the brain, but sometimes if you do it too much, you get some stress. So you have to have a little something different. And so ballet is for me. It's for me what forces in your feet on your toes as you do it. And then actually I had a student who, she was doing dance, and I didn't know this, but she came to me and she's like, you know, I'm interested in this, and because she had an injury and she was recovering from the injury, and so we did a small study to look at how, when you fatigue, how the forces change. And so interestingly, on the dancers we tested, the forces are, you know, when you go up on your toes, they go up, but they're kind of level and they come back down. But as you fatigue, when you pop up on your toe, when people get tired, the force spikes really high. And so that's why we think maybe that's why people tend to get injured when they're tired. But yeah, that's we don't have to keep watching. It's okay. Oh god, it's so long.